action. Finally, the system's display, which is here, can show us a wide array of information. We can see how the fuel is distributed on this page, check on hydraulics or the electrical system, or see if the doors are secured properly, or even what the temperature is in the cabin and cargo area.
We're enjoying the last rays of sunlight in a while. We're going to prepare ourselves and the aircraft for a descent and approach into Kilimanjaro, where you'll see how essential these displays are to us. Go directly close in on second part because of the weather.
1,000 to go. Check.
Thanks, gentlemen.
Impressive. So let me show you another video. Just a second. So the question that arises is, we need to test these things, right? So it's not trivial to develop such kind of systems, and you need to test. So I'm going to present another video. That's the last one, I promise. And that's actually a link to a series of videos by Airbus telling about different things. And the first one is how important is to test the systems embedded in airplanes and the airplane as a whole.
3, 2, 1, stop.
Modern aircraft are highly complex machines with millions of parts, making up hundreds of systems with thousands of interconnections. The design of a new aircraft involves parts created by computation tools, tested in wind tunnels, and on dedicated test benches. And these are indispensable for the development and certification. After years of careful planning, design adjustments, the integration of new materials, and the latest innovations, the aircraft is finally ready to fly. However, in many situations, how an aircraft actually behaves is only really discovered when it takes off. That is why flight tests are essential. Let's look at some examples. In wind tunnels, very low speeds and high Mach number flying characteristics can be identified. But due to various factors, such as scale effect, it is necessary to perform flight tests to confirm the handling qualities of the airplane.
18, 95, 21.
This is also true for ground effect. Consequently, the tuning of the control laws close to the ground for takeoff, landing and auto-land is a hands-on process involving progressive adjustment of the control parameters by the engineers. Aerodynamic coefficients are not known exactly before flying, and there are sometimes surprises. Final tuning of the flight control laws is carried out in flight, mainly at the limit of the flight domain, such as for the high angle of attack protections. The development of the braking system suffers from the same difficulty. The forces applied on the wheels vary with the lift created by the speed, and in ground effect, it is not possible to build a proper computation model. In addition, for some airplanes, the distribution of the weight on the various wheels is not precisely known. Therefore, the tuning and the determination of the performances of the braking system, such as the maximum energy for the brakes, can only be performed by flight tests. The forces on the structure of the airplane may have been underestimated or overestimated during the design phase. They are first confirmed by tests on a static airframe. Then the huge number of load sensors on development aircraft allows the final validation. Even after computations and ground tests, a risk of flutter in the flight envelope up to VD and MD, which are the design dive speeds used for the structural sizing, cannot be totally excluded. A progressive extension of the flight domain by tests up to these speeds is required. Systems also need to be tested in real flight conditions. At the beginning of a program, anomalies may be found due to deficiencies in the design or the installation. The air conditioning system is tested in flight, as the model of exchange with the outside of the fuselage is not sufficiently precise. In addition, the circulation of air inside the cabin is checked in real conditions. We have only reviewed here some of the areas where flight tests are necessary. EASA and FAA regulations impose flight tests in many domains because, very often, it is not possible to guarantee the results by computation or ground tests. The evolution of the certification rules leads to more tests being performed to certify the airplane for all types of operations. ETOPS at entry into service is just one example. In addition, the high complexity of new functions, such as flight control protections, systems to improve comfort, and so on, increases the need for flight test verification. Therefore, the number of flight hours necessary to develop and certify a new aircraft is almost the same as in the past, despite the fact that the engineers have access to more parameters and have more powerful tools for faster tuning. Flight tests are really necessary.
Nice. So what's my point here? What about the software, right? So as you have seen on this video, the development of an airplane is a very complicated but also very controlled process. So you have a lot of effort on design, on developing and testing. And it's increasingly common to have even more software embedded in these kind of systems. And what about the rigor regarding the development, the design, the testing, the verification of these software systems? So that's an area where formal methods may play a very important role. Here I bring a definition by the formal methods era, the FME, which says that formal methods are mathematical approaches to software system development, which support the rigorous specification, design, and verification of computer systems. So, as I said before, it plays a very important role on achieving really high trustworthiness levels when developing software systems in general. And we're not talking just about airplanes, right? So you can apply formal methods when developing different kind of software systems. So here you have some links which you can browse later, showing practical reports and examples on the usage of formal methods across these very big and well-known companies. So we have research groups in Amazon. We're going to have a talk here in SBMF later about this, if I'm not wrong. But you also have research groups in Google, Meta, Microsoft, and many other companies. I think that 2 weeks ago we had in Recife a talk by an engineer from Meta that is working on an application of formal methods and static verification in WhatsApp. And she said that currently the code that is committed by all developers across the world regarding WhatsApp is being verified by a set of tools that they have been working within the last years. And when these tools find potential bugs in the software, a ticket is automatically created to that developer, and he or she needs to address that ticket. And she reported that the set of tools that they have been developing found a very important bug last year. Of course, we don't know what was the bug, but it shows the benefits of the practical application of formal methods, right? Another important thing to say, the Formal Methods Europe is a group regarding researchers, people from industry as well, with interests in formal methods. So if you want to be part of this group, you can apply online and be a member of FME, and then you start receiving notifications about events and various things about the group. So feel free to join. Here is my big picture, my perspective of the area of formal methods. So the central piece is you need to have a very clear and precise definition of the software you want to develop. That's what I'm calling here your formal model. So the formal model is a central element in this picture. What is the formal model? Well, it varies a lot depending on the technique. So the formal model may be a graphical model. The formal model can be a formula. The formal model can be code. But you need to have some kind of precise specification of the expected behavior of your system. This formal model sometimes is created by hand. So some specialists create the formal model from scratch, and then you apply a number of techniques. But in other situations, the formal model is, for instance, generated automatically from code. So there is a tool used in Meta called Infer. And what Infer does is it processes your Java, other code in other languages, and it translates the code to an intermediate representation, and this intermediate representation is then processed to find bugs. So that's an example where you don't need to create the formal model by yourself, where it's automatically created by some kind of tool. There are also approaches where you create a model, like a Simulink model, model in some specific domain, and then some tool translates this model to another model, the formal one. There is also work that addresses requirements. So the work we have done with the University of York, you have this language called RoboWorld, where you write in natural language requirements about the environment of your robotic system. And then there is a tool that translates these controlled natural language requirements to a precise definition of them. So once again, the formal model is a central element in this perspective. When you get the formal model, then there are a number of tools, a number of techniques that you can apply to process this model to, for instance, check some property, to have some guarantees that some undesired behavior will not happen, for instance. I have grouped these techniques into four main classes. You can animate your formal model, so you can kind of simulate your formal model to see whether you have created the proper model. So you may have understood wrongly the requirements, you have created a model that does not represent the expected behavior. This simulation can be performed in some tools by hand. It can also be performed automatically, randomly. Another very important thing that you can do with formal models is verify properties. This verification can be manually, so you can write proofs by hand. This verification can be automatically using tools, techniques like model checking that will create some automated-based representation of your model, and then we'll traverse this representation checking some kind of property. You can also use theorem provers that hopefully will prove your property automatically. In some situations, you will need to interact with these tools, so you will have a kind of a proof assistant that will assist you to prove the desired property. In other situations, you employ translation techniques, so you have the formal model, but you want to have actual code that will embed it in there, like for instance. So there are tools that translate the formal model to some kind of code. So there's a tool called Skate. It has been used by Airbus for quite a while, and it generates C code, and the tool itself is certified in such a way that you don't need to perform unit testing in the C code that is generated, because the tool proves that the C code that's generated behaves exactly as the model that you have created. So you still need to perform integration tests, for instance, but it saves some testing time. So translation is another important perspective. So generate code, generate more concrete models, that's nice. And the last category here of techniques that can be applied to formal models is visualization. So you have this model, you are not entirely sure whether you have properly modeled your problem, and you want to show your model to some specialists, some domain specialists. The specialists from that domain will probably not understand automata, logic, and you want to present some visual representation of the formal model such that these specialists can say, okay, the model is fine, you can proceed. So there are also some tools that address this topic, providing a connection between a graphical visualization and the formal representation of your system. So to summarize, that's my big picture of the area of formal models, formal methods. You need to have a formal specification of the desired property. There are a number of techniques that you can apply. And what I want to do now is, in a very example-based presentation, I would like to illustrate almost of all of these concepts in a very high-level approach. And to do this, I will address a number of languages, which are going to be the B language, which is a language focused for modeling reactive systems, but basically with no concurrency, also typically no time-added property as well. Then I will address another language called CSP, which differently from B, CSP is focused on concurrent systems. So it's a language designed to specify concurrent behavior and verify desired properties. Then I will talk a bit about time and automata, which is another formalism for representing concurrent systems but with time properties. Then I will talk about a format called SMT, which you can use to write logical properties and verify these properties in a number of tools. And the last language I'm going to address in this talk is Galena, which is a language used by a proof assistant called COC, where you can interact with the proof assistant to prove the properties you want. So now I'm going to move to each language, and I will interleave these slides with the actual tools. So I want to be very example-based and very practical. So let's start with the first language. And again, if you have any question, please don't hesitate to interrupt. So B is focused on safety-critical software, but with no concurrency. So it's a language designer for software that we run in a single-threaded basis. No concurrency. Right? There are a number of practical applications of B, particularly in the railway domain. So I have already seen some very nice presentations from some people that work with B industry, and they are very proud to say that there is a line, a metro line in Paris, whose code was embedded in 1998, something like that, line 4, right? 14, yes, line 14. So there's a metro line in Paris whose code was embedded in 1998, right? And it runs until today with 0 bugs found. So they're very proud of this. So that's one example, one practical example of B. There are a number of tools that support using B. In this talk, I'm going to show you 3 of them. I will show Atelier B, I will show you ProB, and I will show this visualization tool called B-Motion Web. As an example, a toy one. So the classical puzzle of Tower of Hanoi. You know this puzzle, right? You have, in this instance, 3 packs, a number of disks. You want to move all the disks from the first pack to the last pack, and the constraints are you can only take 1 disk per time, and you cannot place a disk that is bigger over a disk that is smaller. So the question is, how can you move all the disks from the first pack to the last pack? Here you have my B code, which you cannot read because of the resolution, but I will switch to the tool now. Not yet, just a second. It's better now, right? Okay, so in B, your project is organized into the so-called machines. So you can think of a machine as a component. So here I have a machine called Hanoi. And you can declare a machine has variables. So in this case, my machine has a single variable, and the variable is called Hanoi. And then you have an invariant section where you define properties that need to hold in every state of your system. So that's not something that's true it's just in some occasions. It's true in every possible state of your system. So here I use an invariant to type the variable Hanoi. So on line 12, you have this expression that says that Hanoi is an element, is a member of this. So this is an ASCII symbol for the membership operation. So let's understand what this expression is modeling. This symbol denotes that we have a total function. So a total function says that's a function, so it's a relation, but it's more than just a plain relation. So it's a relation that obeys to the constraints of a function. So for instance, you cannot have an element of the domain associated to two different elements of the codomain. So although I'm not saying this explicitly, this is embedded in the definition of the function. So when I use this symbol, the tool implicitly generates this condition that needs to be checked. So you cannot have in any state an element of the domain of this function associated to two different elements of the codomain of this function. Besides a function, I said that's a total function. So as a total function, it means that every element of the domain needs to be mapped to some element of the codomain. And what about the codomain? The codomain, here I say that I have a set of the elements 1, 2, and 3, and I use this definition that generates all subsets of the set containing the numbers 1, 2, and 3. So it's similar of a power set definition. Here I'm using fin just to say that I'm considering just finite subsets of this set. In this case, all sets are finite because the interval between 1 and 3 is finite. But using fin here helps me to prove some properties, because if I have used instead pole, which is the operator for all subsets, even the infinite ones, I will have some additional properties to prove, which I don't want to. So this, to summarize, represents this set of all total functions from these sets that you can create. And what I'm saying here is that Hanoi is one of these functions. So in every state of my system, Hanoi needs to be one of these possible functions. So one thing that's quite different here is that it doesn't resemble like programming, right? It's not similar to C, Python, JavaScript. It's more script mathematics. So you're specifying what the desired behavior in a very high level way. Another invariant that I have here says that for all two pegs, P1 and P2, where P1 is one element of the domain of Hanoi, and P2 is another element of the domain of Hanoi, and P1 is different from P2. So for every P1 and P2 where this holds, I have that the intersection between Hanoi P1 and Hanoi P2 is equal to the empty set. So what I'm saying here is that Hanoi is a function from pegs to disks. So if I select two arbitrary pegs, which are not the same, so peg 1 and peg 2, if I apply Hanoi to this peg, I get the disks that are on this peg. And the intersection between these sets is empty. In other words, I cannot have a disk that is at the same time two different pegs. So that's the motivation for this. I forgot to say, my abstraction here about the problem is that you know that set is a structure with no order and no repetition information. And in the Hanoi problem, you have some order notion because you have the order of the disks in a particular peg. What I'm assuming here is that when I retrieve a disk from a peg, this is going to be the smaller number in the set, right? So this is something that I implicitly assumed in my abstraction. So after setting After defining properties that I want to hold in every state of my system, I come to the initialization. So the initialization is basically defining the initial state of my system. So that's the place where I need to say what is the value of each variable of my machine in the initial state. And here I'm saying that Hanoi is this set where I map 1 to the set 1, 2, 3, 2 to the empty set, and 3 to the empty set. So I'm here saying that I have all pegs, all disks in the first peg, and the other pegs have no disks. Suppose that I do something wrong, like this. If I do this, I'm saying that I have the disk 1 at the same time on in peg 1 and peg 2. If I open ProB, for instance, which is this other tool that processes B specifications, and I load this model, when I execute the initialization operation, unfortunately I cannot, as far as I know, increase the size of this font here, so you will need to believe me. But when I click on initialization, you can see a red button here, and let me copy. Can I copy this? Yes, I can. Okay, just a second. So the output of the tool was that this invariant is not true in the first state, because I said that I cannot have a disk on 2 pegs at the same time, and the tool is warning me that I have defined an initialization state, an initial state, that does not fulfill the invariants that I have specified. This is a very simple example, but imagine you have a very complicated system where you need to configure a lot of variables. The tool can check for you whether your configuration is not violating the constraints that you presume from the system. Okay, so we have an initial state. And how can I reach all the states in my system? I do this by performing operations. Here I have a single operation called move, and the move operation has 2 parameters called from and to that represent the pegs I'm moving from a disk and the peg I'm moving to the disk. So from and to are elements of the domain of Hanoi. I also have here that from and to need to be different pegs. So I'm not modeling here a situation where you take this from peg and you put it back. So when you take some of this from peg, you need to move it to a different peg. Additionally, if I'm doing this, I presume that the peg associated with from is not empty. Well, you are taking a disk from this peg, it cannot be empty. And if the peg you're moving the disk into is not empty, so if you're moving a disk to a peg that already has some disks, so if this precondition, if the antecedent of this implication holds, the minimal value from the from peg needs to be less than the minimal value of the to peg. So that's constraining such that you cannot place a bigger peg or a smaller one in my abstraction here. So if all these preconditions hold, you can perform the operation safely. So that's the idea. And what is the operation? The operation Hanoi, the operation move, is going to update, that's the meaning of the symbol here, is going to update the variable Hanoi. And how this update is going to be performed? Well, I'm going to update the mapping associated with the from peg and I'm also going to update the mapping associated with the 2-pack. And I do this basically removing from this pack the disk I'm moving, and I perform a union between the set of disks I had before the 2-pack with the disk I'm currently moving from 2 to from. Sorry, from to 2, right? So have you understood? Is it clear what I'm modeling here? Obviously, there are a lot of syntactic details here, but hopefully you have understood the main idea here. So as you can see, this is not close to programming, as I said before, but this tool called LAB can actually generate C code. So what's the magic? There's no magic. The idea here is that you first create a very abstract mathematical logic-based specification of your system. You check this, and when you are confident that your specification is correct, you need to perform a set of refinements. And by these refinements, you should, for instance, change the type of this variable Hanoi, moving from a type from discrete mathematics to some concrete type that you typically have in C, for instance. So you need to represent these sets, for instance, using arrays. And when you define a refinement, you need to prove that the behavior of your refined specification is consistent with the behavior that you define at the more abstract level. So after performing a set of refinements, then you should hopefully reach a very low-level specification, and this low-level specification can be translated automatically by the tool producing C code. And then you can use the C code in your system.
I would like to know if lines 34 and 35 happens simultaneously.
Sorry?
Excuse me. I would like to know if lines 34 and 35, they happen simultaneously?
Thank you for the question. So let me go back here. Yes, that's a very interesting question. Thank you. So the question was, these two lines 34 and 35, do they happen simultaneously or whether they happen in some sequential fashion? You're right, they happen simultaneously. In the abstraction level, you can see an operation as an atomic block. So everything within an operation happens at once. When you move from this abstract definition to a concrete implementation in B, then you need to introduce sequential operations. So in the low-level definition, you will need to create a temporary variable, and you will need to guarantee that this temporary variable is properly handled. And when you do this, there are a number of proof obligations that are generated to check whether you have done this correctly. Right? So the idea here is to be very high level. So the focus is, I'm not thinking yet in how I'm going to implement this. I'm thinking about how can I properly specify the expected behavior. Then I will think how I can implement this in C, for instance. Okay? Any more questions?
So I was wondering, well, you said that you start from this high-level model and you start to climb down, going down into, well, more low-level models. So you can always use the high-level model to check the lower levels, something like that, to keep some consistency.
If I understood the question correctly, yes. So you create a sequence of refinement steps, and each refinement you need to prove that the result of the refinement is consistent with the previous one. But you can have multiple machines in your project, and one machine can use a machine from another component. That's possible, but each machine has its proper refinement stack. So each machine is refined separately, and you see, you access a different machine as an interface. So when you invoke an operation from a different machine, you're not bothering how this operation is going to be implemented. So there is no refinement consistent between different machines, but concerning a stack of refinement steps of a single machine. Was that your question?
Yes, so you always keep the high level model all the time to bring the whole process of generating.
Oh, right. So maybe I understood incorrectly your question. Well, when you use B, you may have code that is generated using this idea, but you can also integrate your code into code that's not going to be verified. So you're not going to verify the whole system. So you may have machines that are not refined, and in the actual code, you assume that these functions, these operations, are provided by some API, and you're not going to test, refine, or check this API in the B level. So that's the reason why, in the end, you still need to test your system because of integration with code that has not been developed in this system and checked in this system. So you can integrate verified code with code that's not verified. That's possible. But this integration needs to be tested. Okay. Yeah.
Excuse me, I have two questions. The first is the goal of the specification is to optimize the code or just verify if it will work. For instance, you check if the same disk is replaced with the same position it was before, but it's possible to create a code that works, will solve this problem, but this operation happens. So the goal is to optimize or just see if we'll solve the problem.
Okay, I would say that in the machine level, you're not very concerned with optimization because you're typically far from actual code. So for instance, in the very low level, you typically need to worry about the data structure that you're going to use to provide efficient computation. But regarding this move operation, yes, it's possible to define the move operation without that precondition that prevents taking a disk from a peg and just placing it back. I just need to delete the condition, this particular condition from the preconditions, and this will be allowed to happen.
The goal is not optimization.
No, in general, at this level, so the machine level, the goal is to specify the expected behavior. And the concerns about how you're going to actually implement this will happen when you reach the implementation. So this is called a machine. There is another concept in B, it's the implementation. And the implementation is the least refinement of a machine. And in the implementation level, then you have your optimization concerns. So another example here, this is performed as an atomic block, so everything happens at once. But in the concrete implementation, you will need to perform a sequence of operations. And how are you going to do this? Are you going to create an auxiliary variable that will consume some memory to do this? Or are you going to implement this in another way that, well, will use less memory, but it will be less time efficient? So the concerns about optimization is typically not at the machine level, but in the implementation level.
Can I do another question, please?
Yes, sure.
Sorry, my English is horrible.
If you want to ask in Portuguese, that's no problem. I can try to translate it in English, so feel free.
Tá, obrigado. Eu queria entender uma coisa. O código aí dessas restrições, o objetivo dele é verificar o código na tempo de compilação. Você vai compilar o código, aí passa isso e verifica, tipo, esse tipo, lendo o próprio código, existe essa possibilidade de violar alguma das restrições, ou não, está executando o código e em tempo de execução vê, tipo, opa, violou alguma, não pode mais.
Okay, so translating to English, I think your question was whether the purpose here is to perform these checks in a static way, so during the compilation of this code, whether these checks are performed dynamically when I run the code. Again, the machine level is not the level where you're thinking about actual code that you run in the system. It's a specification level, so you are defining the behavior that's expected from your system. So I will show something about the properties that may clarify some things. Is that right? Yeah. So we have been talking about properties. But what are these properties? What are the properties that we have here? I will go back to this screen. You cannot probably see, but there is an option here called Generate POs, so Generate Proof Obligations. And when I do this, it generates 8 proof obligations. What are these proof obligations? These are the obligations that I need to prove to ensure that my specification of the move operation, that they meet the invariants that I have defined. So the idea is, as an invariant, you specify some property that you want to be true during all states of your system. It is a guarantee. We don't know yet, because it depends on how you implement the move operation. For instance, I could have, by mistake, written from here. This would be a bug, this would be an error, and the consequence of this is that when I generate these proof obligations, there would be a proof, that there would be an obligation that I would need to prove, that it would not be possible to prove it, because I have done something wrong in my specification. So trying to prove this obligation and failing would probably show me that I specified incorrectly the system, and then come back here, and write the correct specification. And after doing this and proving all proof obligations, this would guarantee that this specification meets the properties that I defined as invariants. But I'm not running this code yet. This code is high level. Then I would need to refine this code to have another code that will use arrays, loops, things like that, as we are familiar with. And then I would need to prove that this concrete code is a correct refinement of this high-level code. And then the concrete code would be translated to C, and the C code would be embedded in the system. And so what would be the guarantees in such a scenario? I would have some kind of guarantee that the C code that was generated, it meets the properties I defined. So these properties, they are not being verified in summary, they are not being verified during the execution of the system. They are actually verified while I'm creating the code. When you write C code, you don't have typically preconditions, right? You have a function. The precondition here will become if clauses in your function, in your C function. So the role of the preconditions here is to check whether you have defined the conditions you need to check in your actual code. But you do this here in a more abstract way. Have I answered your question? Great. Yeah.
I have to ask, if you remove that second part, line 35, presumably you would still preserve your environment, because you formalize as an environment the fact that a disk is not at the same time on 2 different pegs, but you haven't I can't help but notice that you haven't written another obvious invariant, which is that every disk is on some peg. So I was wondering, usually the problem of the Tower of Hanoi is to search for a sequence of operations that moves all the disks from peg 1 to peg 3. I'm wondering if that particular invariant actually plays a role in searching for the sequence of operation in a way that's different from these other invariants I have in mind.
Thank you. You're totally right. There is an environment missing here. I didn't prove it because it was a bit more scarier than this one. But you're right. I should write an invariant to guarantee that disks do not go somewhere. Yes, I should do this. But this invariant is not exactly related to find a solution. To find a solution, I could have this other invariant here. And what this invariant here says that I'm saying that there is no state where all pegs are in the, all disks are in the third peg. So this property can be violated, assume that there is a valid sequence of operations of call and move that will move from the initial state to the standard state. And I can check this by switching to Probe, reloading my model. Oops. Oh, sorry, there's a tab open here. So let me reopen. There are a lot of things to cover, but in Probe, you can perform model checking, for instance, and by model checking, it finds a invariant violation, and it provides you with a trace, the sequence of operations that move you from the initial state to the state where that invariant is violated, and this sequence of operations is a solution for the puzzle. Yeah? Any other questions? Unfortunately, I'm not sure whether I'm going to read, but if I come back here to Probe, so I have generated 8 proof obligations, as I said before, and 16, 17, oh, right, because let me comment these. So 8 unproved proof obligations. So Probe comes with some theorem provers, a custom one, and you can also integrate other tools like Z3 that I'm going to talk later. Actually, there are a number of proving strategies here. What it says here is automatic force 0, force 1, force 2, and force 3. These are 4 different strategies for proving properties automatically. Well, you know that these properties, in theory, they are, you may write properties that cannot be proven. They are undecidable in theory, some of them. But basically, we have encoded here some heuristics that will try to prove the proof obligations using different strategies. The highest force implies that they are employing strategies that are more time consuming. So you can kind of control this. If I select force 3, it's running, it's finished. It left 2 proof obligations that have not been proven. And what you can do here is that you can open an interact proof. You can inspect the proof that has not been proven, and you can write your proof. So you can add hypotheses, you can perform induction, you can perform test analysis, you can invoke the automatic proof that's embedded in the tool, you can integrate these with all the proof assistants and proof theorem provers. In this particular case, the proof is not very difficult. If I do this, I was just clicking some buttons that perform some classical logical manipulations. And now this proof obligation has been proved. Now just one proof obligation is yet to be proven. So how this has been done, how this tool has been used in practice. They are designing the code that's going to be embedded in the Paris Major Line 14. So they write a specification in B. They validate that they have properly defined the specification. They generate thousands of proof obligations, and they work to prove all of them. The papers about this tool say that currently, if I'm not wrong, about 80% of the POs, of the proof obligations, are typically proved automatically. And the other 20, they need to be proved by hand. So some expert needs to interact with the tool to prove the remaining proof obligations. And I have already heard that what they do is that they hire people with the background to prove this. So it's something that costs some amount of money, but as a consequence is that you have code specification where you are more confident.
So just to give more information on this topic, I saw a talk last week by David Ehar, who works at ClearC, and he had a data point in his slides that currently at ClearC, which is a company that uses heavily, their business model, the main thing is about using Atelier B to prove things about various systems and so on, is that the cost per proof obligation that has to be proven manually is about 35 euros per proof obligation on engineer's time.
Great. Okay. I think I will just show another tool here, which is BMotion Web. So I have to show you B. You can use Pro-B to draw the whole state space, which is possible within this example, which is quite trivial. It has 28 states and 79 transitions, but for actual systems, you can't generate the whole state space, but it's possible using Pro-B. And what about the BMotion Lab? So BMotion Lab is another tool. BMotion Lab. BMotion. Examples. So what is BMotion Lab? BMotion Lab is a tool where you can create graphical representations and connect these graphical representation with your B code. So what is executing here is not a C representation of my machine, but actually the code in B that I have written. So that's a very classical lift example, where you have a building with 3 floors and you have a lift. And what you can do using this tool, you can interact with your model by clicking on the operations, and you see how these operations change the graphical interface. So for instance, here I can showing the lift moving up, or for instance, the lift stopping, someone requesting for a lift on the 3rd floor, the door opening, and things like that. And this visualization idea, as I said before, is very interesting if you want to validate your formal model with some domain specialist that's not familiar with the formal specification that you have. So imagine you have a very complex system. There's an interesting example here of a landing gear system. And you have here a visualization of the circuits that we use, and you can validate with the domain specialist whether this makes sense. And then when the specialist says, okay, you have modeled properly the system as I would expect it to behave, this is somehow some guarantee that your machine specification is right. So it's a validation step. And then you should proceed by refining this machine to reach the C code that you want to embed in the actual system. That's another interesting tool called bMotion Web for providing visualizations for B models. Okay, I think that's all I had to say about B. Do you have any other questions concerning B? Can I move to the next language? We are going to have a break, I think, in 20 minutes. So I think I can talk about the next language, which is CSP. So B, although in the machine, an operation is seen as an atomic clock, so you have a number of computations that are performed at once. In the implementation level, you do not have concurrency. So everything needs to happen sequentially. CSP is a specification language whose primary focus is on specifying the behavior of concurrent systems. There are a number of practical applications of CSP. There is this paper that has been published a couple of years ago mentioning a number of applications of CSP in industry, ranging from test generation for concurrent systems up to control systems of nuclear submarines in the UK defense. So there are a number of applications of CSP. And we are going to have, I think, 2 presentations in SBMF with applications of CSP on Thursday, if I'm not wrong. Concerning tools, there is this tool called FDR that has been developed in Oxford. That's one tool that you can use for checking properties of concurrent systems specified in CSP. There are actually 2 dialects of CSP. There is the one that's called CSP-M. This M stands for machine readable. CSP-M is the language, is the version of CSP that has been developed and maintained in Oxford, and FDR is for CSP-M. But there is also another dialect of CSP called CSP-Sharp that has been developed in Singapore. So there is another tool that supports CSP-Sharp. The tool is called PAT. It's Process Analysis Toolkit. ProB, the tool I showed you before about B, can also load CSP-M models. So there are a number of tools, but here I'm going to talk just about FDR. And as an example, the classical one, the dining philosopher's problem, which is a metaphor for a concurrent system with concurrent components that access some shared information. So the notion here is that you have a table, you have a number of philosophers, and each philosopher behaves as follows. He sits, he takes 2 hashi, then he eats, he thinks, he puts down the hashi, then he gets up and does something, and then he repeats this. So as a metaphor, each philosopher is a metaphor for some component of their system that performs some computations, but there is some computation that needs to access some shared resource. And the shared resource here is the hashi, which is used by the philosophers to eat. So since you have a round table, this, for instance, this hashi is shared by these two philosophers. The problem here, this is a classical problem to show the consequence, one consequence of concurrency, that is the deadlock. So if each philosopher takes the right hashi first, before getting the left one, what will happen is that every philosopher will have just a single hashi, and he will be waiting for the other one to be put down on the table, but everyone is going to be waiting for another one, and then you have a deadlock, because each component is waiting for something to be done by the other component, and the system deadlocks. And this is a kind of problem that's very difficult to catch by testing, because there are a huge number of combinations that does not reach the deadlock. And as you know, if you're testing, you will probably run a lot of tests, and the deadlock will happen just when you deploy the system on the first day, right? So here you have the CSP specification for the dining philosophers problem. I will switch to some editor such that we can see this text bigger. Is that fine? Should I increase the font? Is that fine? Yeah, it's okay. So this code, differently from the previous one, this code is not, I had not written this code. This code has been written by Bill Roscoe from the University of Oxford. And I will try to briefly show you this language called CSP. So in this language, the two main concepts are channels and processes. So a process, you have here this field. Field is denoting the philosopher, and that's the process called field. A process performs a sequence of computations, and the computation here is abstracted by what's called as an event. So channels define communications across processes, and then you have events. So first we have, concerning the philosophers, we have these channels: sits, eats, and gets up. And these channels, they communicate a value that belongs to field names. And field names is a set of numbers ranging from 0 to n minus 1. So in this example where n is 2, basically field name is 0 or 1. So when the philosopher, for instance, 0, is performing his computation, the first event that will happen will be sits 0, representing that the philosopher 0 has just seated. So as you can see, this language is very abstract, and that's the reason why we call this as a specification language. It's not, you're not representing how you're going to implement the concurrency, but where you want to reason about the concurrent properties, the concurrency properties, to see, for instance, whether your system has some kind of deadlock. So the philosopher sits, then he performs peaks. And peaks is a channel that communicates two values. A value representing the philosopher that is peaking, and another value representing the fork, the hashi that's going to be peaking, right? So let me switch to the tool. So that's the so-called label transition system for the first philosopher. The red circle denotes the initial state of the system, and the arrows represented transitions between the systems. So this philosopher, the first action that he performs is sits 0, as I said before. Then the philosopher 0 picks the fork 0. Then the philosopher 0 picks the fork 1. Then the philosopher 0 eats, puts down the fork 1, puts down fork 0, and then the philosopher gets up. So, field denotes a process indexed by a number representing the philosopher. And in this particular code, I have just 2 philosophers. Right? I have another process here called fork. And fork represents the fork. And I have a choice here, denoted by this symbol. And what is the choice that we have here? A fork can be picked by 2 different philosophers. The philosopher that is on the right of the fork and the philosopher that's on the left of the fork. So basically here we are saying that fork offers us choice between these 2 behaviors. And the first one is that the fork I is picked by the philosopher I, then it is put down. But another option is that the fork I is picked by the philosopher I minus 1. Right so far? Now, I have fields. What is fields? This symbol here represents what we say interleaving. So we have different components running in parallel, and there is no synchronization between these components. So basically, I'm saying that fields is the interleaving of all philosophers that I have in my model. Whereas forks is the interleaving of all forks that I have in my model. And finally, the system itself is composed by the parallelism of all philosophers, all forks, but here I have some kind of synchronization. And the synchronization here means that a fork can only be picked by a philosopher if the fork is in a state ready to be picked by that philosopher. This represents a situation that when a fork is picked by one philosopher, it's not ready for being picked by another philosopher until it's put down by the first one. So that's the place where we represent the synchronization between the concurrent processes. So as you can see, it's a very different language from B, and the focus here is providing to the user operators to model concurrent behavior, synchronization, sending messages, sending messages across different processes. Besides that, we can write assertions to check classical properties, like for instance, whether my system is deadlock free. So if I open this specification in FDR, and I click check, it's going to fail. So it's going to say that this process has a deadlock. And I can debug, and it provides a trace, a sequence of communications that lead me to the state where the deadlock is. And then I can reflect about my specification and see which changes I should perform to prevent the deadlock. In the Dining Philosophy's problem, there is a classical solution, which is to take a single philosopher and make this philosopher picks the forks asynchronously in a different order regarding the other philosophers. So that's what called the asynchronous system, and this one is deadlock free. So that's CSP. So suppose you are going to define some system. This system is going to have a protocol and this protocol is going to be sharing messages across different components of our system. You can use CSP to model this protocol and check whether your communication protocol has a deadlock. So that's the purpose of CSP. It's important to say that FDR performs this verification using model checking. So these, you cannot see these, but you have here the graph for the philosopher zero that I showed before, but I can also ask the tool to show the graph for the entire system. That's the graph for the entire system when you have just two philosophers, right? So as you can see, it's far from being trivial. And you can use it to check whether the system is deadlock free or not, as I have just done before. But what's the problem here is in classical model checking, which the idea here, it typically suffers from the state exposure problem. So this tool, at least as I'm using it, it's not perform statistical model checking or symbolic model checking. So as when this graph becomes really big, this tool cannot traverse the whole graph to check the property. So that's the pros and cons. An advantage of this tool is automation of the verification. So you click a button and you get yes or no. But the downside is that scalability is a problem. So what people try to use when they're using FDR is to analyze some property in a compositional way. So instead of verifying the whole system, you verify parts of your system, and each part is sufficiently small, and then you prove that by verifying the smaller parts, you can conclude that the whole system is, for instance, deadlock-free, but with but with no direct execution of the whole system itself. But compositional thinking is something very important when you're using tools like FDR.
Sorry, I may have missed that, but did you say that this is for finite state machines, or does it also cover infinite state machines and deploy some unbounded model checking techniques?
As far as I know, bounded state machines, finite state machines, but there may be some extension. If you create a process whose LTS is not finite, the tool is going to keep running. So it's bounded model checking. Do you have any other questions about CSP? No. So I think it's time for a break, and then we resume seeing other formal languages.
Yes, thank you very much, Gustavo, for your first part. Let's give some applause to Gustavo for this. Thank you.
Here using the British cross. So there basically so you have 4 files. The first one, the bridge is almost falling, so we have 2 files at the same time. left to right, for instance, it needs to example that you want to model and reason about. Right? Have you ever heard about this puzzle before? No? Yeah, okay. I'm going to switch to UPAL. So here I have a description of the problem. One thing that's different from UPAL and the other two languages is that in UPAL you model your problem graphically. So in B and CSP, you're employing a textual language, and here you can create model your example using automata. How it's done here? There are two automata. There is one automaton representing a Viking, and there is another automaton representing the torch. In this automaton, this state here marked as unsafe is the initial location of this automaton. You have transitions between states, and the transitions are guarded by conditions. So the labels, the green labels are the conditions. I think that's better. L stands for the torch. When L is equal to 0, it means that the torch is on the left side of the bridge. Right? When L is equal to 1, it means that the torch is on the right side of the bridge. So remember, this is automata modeling the Viking. So when the torch is on the left side, this transition becomes enabled. And when this transition is triggered, this take event needs to occur. And the event take models the notion of the Viking taking the torch. When this transition is performed, there is an action, and this action assigning 0 to Y means that you are resetting a clock. So Y has been declared as a clock, and basically when you move from unsafe to this state, this target state, you reset the clock, and now the time regarding this clock starts to run. There is another file here with some global declarations. So you have here the channels take and release to model the torch being taken and the torch being released. You have this L that I mentioned before, which is to model the sign of the torch regarding the bridge. And there is a global clock called time. Besides these global declarations, you have local declarations within each automaton. And considering the soldier, the Viking automaton, you have this clock named Y. So let me go back here. So you start on the state unsafe. When the torch is on the left and it's available to be taken, you can take the torch, you move this state, and you reset the clock Y. Then you can only move from this state to this state when the value of the clock is greater or equal than a given delay. And this delay is defined here, concerns the time required to cross the bridge by each Viking. As I said before, each Viking has a different speed, and it implies that the time required to cross the bridge is different. So when the clock is greater than the delay of this Viking, you can move from this state to this other state, and the torch is released. If the Viking is on the safe state, so safe means that this Viking has crossed the bridge and he's on the right side. If the torch is on the right, he can take it again, and he can go back to the unsafe location. So here we reset the clock again, we move to this state, and when the clock is greater than the delay, you release the torch and you go back to the unsafe state. So this automaton is modeling a Viking crossing the bridge from the left to right and from the right to left. Is that clear? Note that this automaton is parameterized by this delay, and when I'm declaring the system, I instantiate the automaton, providing a concrete value for the delay. So I think that's very interesting because an automaton in this tool is a parametric definition, and you create instances of the automaton, and the instances of each automaton is going to be run in parallel. So here you can also model concurrent behavior, but with the additional modern of time property. The torch is also represented by an automaton. This is the initial location of this automaton. So the torch initially is free to be taken. When there is a request by a Viking for the torch to be taken, it moves from this state to this state. And if two Vikings are requesting the torch to be taken, it moves to the state 2, denoting that two Vikings are at this moment crossing the bridge, and both Vikings are carrying the torch. If the crossing is going to be performed by a single Viking, it can move from this state to this state, denoting that just one Viking is carrying the torch. This symbol here denotes that, I'm not going to get into all the details, but there is an urgency associated with the transitions of this state. When you are on the 2 location, you should have 2 releases to the torch become available again. So the 2 occurrences of the release event denotes that both Vikings have released the torch. And when this is done, the value of the global variable L receives the 1 minus L. So remember that the torch is initially 0. So when the torch goes to the right, its value becomes 1 minus 0, so it becomes 1, denoting that the torch is on the right side of the bridge. When the torch moves from the right to the left, you're going to assign to L 1 minus 1, and it becomes 0, denoting again that the torch has come back to the left of the bridge. Is that clear? Okay, so in this file, we instantiate we create one instance of the solid automaton for each Viking, and we also create an instance of the torch automaton, and we say that the system is composed by the parallel, is represented by the parallel composition of each automaton. What is really nice in Opal is that you have, just a second. Why this simulator is not available? Maybe I have done something wrong. Just a second. Right. So you have this nice simulator where you can simulate the execution of your system to check whether you have properly modeled your problem. So there is a random simulation where you can just click random, and as you can see, the events will keep happening, and you see on the right side the current location of each automaton, and then you can check whether you have properly modeled your problem. Besides random simulation, you can perform the simulation by yourself. So you can say that initially Viking 1 is going to take the torch, and you can select the amount of time, and this is continuous. So if I click here between 4 and 5, this is going to denote that this Viking has taken this torch at 4.something time units. Besides the concrete simulator, you also have a symbolic simulator, and this tool offers a number of techniques to both specify time-of properties and verify these properties. And here you have different techniques employed concerning FDR. So here you have unbound model checking, you have symbolic model checking, you have all the kind of techniques used under the hood. Do you have any questions about this tool?
I was just curious about, can I specify the goal of the system or something like that? Because you model the constraints, you talked earlier about the goal of the Vikings problem, where I actually want to all the Vikings to move to the right side. So can I specify a goal to see if the system can achieve that?
Sure. Let's see whether I can increase this font size here. So there is support for temporal logics, like I don't know whether you're familiar with linear temporal logic, computational tree logic. So you can specify the properties of your system using this temporal logic, and you can run the tool to verify whether these properties hold in your model. So yes, you can do that. So basically, here you have that eventually in the future the Viking 1 is going to reach the safe location. So basically this formula here is stating that Viking 1 can reach the safe location. This other property here is saying that in every possible execution of the system, it is going to be true in every state that you do not have a deadlock. Right? So yes, you can employ specific logics for reasoning about time and use it to verify this. Okay. All of these tools have this common goal, that is, you create your formal model and you perform some kind of verification. So they all have some support for verifying properties. Okay. Do you have any other questions? No? Okay. So let's move to the next one. In this second part, I will probably spend a lot of time in the third language, which is Galena in Coq. So I'm going more quickly regarding UPAL in Z3. Okay, another very popular formal notation is the SMT lib standard. So SMT-Lib is an international initiative aimed at facilitating research and development in satisfiability modular theories. So that means you want to determine whether a mathematical formula can be insatisfiable. And there are a huge number of tools that address this problem with different perspectives. Here I'm going to talk about one. The link is wrong, sorry about that. It's not a TLB. Although you can integrate Z3 with a TLB, my intention here was to provide the link to Z3. So Z3 is a SMT solver that is currently open source, and it has been developed mainly by Microsoft. And what you can do is you use this particular notation, the SMT-Lib standard, to write mathematical formulations, and then you can ask the solver to check whether these formulations are satisfiable. So in this first example, I'm modeling this linear system and using Z3 to check whether this system has a solution. How is this done? So on the right side, you have this code, this standard. So I'm declaring two variables. Both variables are real numbers. And with this assertion, I introduce constraints in my model. And I'm saying here that 3x plus 2y is equal to 6. So I'm using this postfix notation to represent this equation here. On the next line, I have another assertion to represent the next equation. And when I execute the command check sat, Z3 is going to verify whether these all assertions I have created, whether they are satisfiable. If they are, I can request the tool to provide me with an instance that satisfies the model, and this is performed by the get model command. It's important to say that this syntax and this command is part of this standard. So if you are developing a tool, a solver to this standard, you should provide support for the same commands. So if I go to the terminal here, I have here a file with the code I have just shown you. And if I run Z3 on this file, it says that my assertions are satisfiable. And when I ask for a model, it provides me with this instance. So if y is assigned to minus 3 divided by 13, and x is assigned to 28 divided by 13, this valuation satisfies both equations. So as you can see, it's not just about logical properties, so that's why it's called an SMT solver and not just a plain SAT solver. But you can also use Z3 to reason about logical properties as well. So here I have an example where I declare two Boolean variables, P and Q, and I create two assertions saying that P implies Q and Q implies P. So P if and only if Q. And as you may know, to satisfy these formula, both P and Q are false, or both of them are true. But then I add a second assertion saying that P is not equal to Q. So is there a way to satisfy this formula where P is not equal to true? Basically, that's what I'm asking Z3. And when I run Z3 on this example, it says unsat. So you cannot satisfy this. Since you have first predicate logic is undecidable, Z3 has three possible outputs. It can say sat, so it knows that you can satisfy, and you can ask it to provide a model. It can provide you with unsat, so it knows for sure that's not possible to satisfy your assertion, but it can also return unknown. So there is a time limit that's configured, and if you reach this time limit, you get as a result unknown. So I don't know whether this is satisfiable or not. So as you can see, Z3 is quite low level. So you are in the level of checking satisfiability of mathematical formula. So Z3, for instance, can be used integrated with all the tools, as I mentioned before. So when you're using a TLAB and you have a proof obligation, you can integrate a TLAB with Z3 to use Z3 infrastructure to try to prove that proof obligation for you. Okay? So there are also a number of applications. If you see this link here, you can find a number of applications, practical applications of Z3. There are a number of them in Microsoft itself, of course. There's a tool that has been developed there. And now it comes time for the last one. As I said before, I'm going to take some time here. So Galena is a general purpose specification language. It's a functional language, quite similar to Haskell, but with some important differences. And the goal here is to model some problem, improve properties, but differently from Z3, the proofs here are constructed in an interactive way. So Z3 is what is commonly called a theorem prover, an automatic theorem prover, where you ask and it answers whether it's true, it's false, or it doesn't know. That's the general purpose. When you're using Coq, as I'm going to show here, the style is quite different. You're going to interact with the proof system to prove the property that you want. So you need to guide the tool to the kind of manipulations, the logical and mathematical manipulations the tool is going to perform. There is also some support for automation. I'm going to highlight these, but a different level. It's not the same thing as Z3. So Galena is this functional language, and Coq is the tool that can process this language. As an example, I'm going to use the notion of a dictionary, a map. So you want to map integers, some integer to some string, and you want to create a dictionary. Classical example would be the integer would be a number that identifies uniquely someone, like here in Brazil, the CPF, and the string is going to be the name of that person. In this example, my dictionary has this interface. So it has 5 functions. There is a function called clear that, provided the dictionary yields an empty dictionary, there is another function called isEmpty that says whether a dictionary is empty or not. There is a function called size that yields the number of elements in my dictionary. There is a function called insert that receives a key, a value, a dictionary, and provides as a result, an updated dictionary. And there is a function called find that provides the key in the dictionary, yields the value associated to that key, if there is this mapping in the dictionary. So for those who are familiar with Haskell, who have the maybe in Haskell, here this option is the same idea of the maybe in Haskell. So basically this function find, it may yield none, so there is no mapping to the provided key, or it may yield some value, so the value mapped to that key. In my example, I'm going to implement the dictionary using binary search trees, because dictionary is an abstract data type, which can be implemented using different data structures. So you can use hash tables, you can use linked lists in theory, you can use binary search trees, you can use AVL trees, red-black trees, you can use very different data structures to implement this notion. In my example here, I'm going to use binary search trees to implement the notion of dictionary. Is that clear so far? Yeah.
What is the logic behind the language? Is first order logic?
It's high order logic. But it's not classical high order logic, its intuition is high order logic. But we can talk about the details, because there is another very popular proof of system theorem prover called Isabelle, whom you are familiar with. So the logics are a bit different between them. So yeah. Here, the focus of course is intuitionist logic, which is not the case of Isabelle. Okay. So let's go to the tool. Let me increase the font here. Is that okay? Okay. So here's my code. In this code, I will have both the specification of the abstract data type and the implementation of this abstract data type using binary search trees. And in my implementation, I will prove that my implementation is correct concerning the abstract specification. Here I have a lot of imports to import in the scope definitions from the prelude of Cork. So I want to reason about strings. This LIA library is an a proof automation library that can solve a subset of first order logic which is decidable. I will illustrate this later when I'm doing the proofs. There is a tactic called LIA, and it can solve automatically a particular subset of first order logic. I want to reason about natural numbers as well. I want to reason about Boolean variables as well. I want the notion of lists. And this extraction, I will illustrate towards the end. That is, I can, for instance, generate Haskell code from my Galena specification. And then I can use this Haskell code in my actual software. First, I create a module type. A module type defines, it's said here, the interface of my abstract data type. As an interface, it's not going to say how the type is implemented, but what are the main properties associated with this type. Here I say that keys are natural numbers. I say that values are strings. And dictionary is any possible type of the Cork language. So I'm not saying here how the dictionary is going to be implemented. This decision is done later when creating the data structure. I need to have a definition for the empty dictionary, and the empty dictionary should be a valid dictionary. What is the actual empty dictionary is not clear, it's not defined here yet. Next, I define the operations that can be performed concerning a dictionary, and these are precisely the ones that I have presented before on the slides. So you can clear a dictionary, query whether it's empty, know its size, insert the mappings, and find the value associated with a given key. Now, I define the expected properties of any valid dictionary implementation. So the properties that are going to be defined now, they should hold in every possible implementation of my dictionary interface. And here, since I'm in an abstract level, these properties are defined as axioms. And when creating the implementation, I will need to prove these properties concerning the implementation decisions I have taken. The first axiom says that for any dictionary, if I clear the dictionary and after that I query whether the dictionary is empty, this should be always true. It's quite expected. This next action says that for any dictionary, after clearing it, its size should be equal to 0. So basically, the axioms are relating the functions to establish the expected behavior of them. For any dictionary, if it's empty, so if I ask whether this dictionary is empty, if this is true, this means that D is the implementation of the empty dictionary. And if the D is the implementation of the empty dictionary, is empty should yield true as well. Here is a similar action. So for any dictionary, if it's empty, it's size 0, and if it's size 0, it's empty. A more interesting one is that for any dictionary, if it's empty, this implies that for any key, if I try to find the mapping associated with this key in this dictionary, this will always yield none. Well, the dictionary is empty, so there is no key in the dictionary, so any find should yield none. This one says that for any dictionary, any key, any value, if I insert this pair key value in the dictionary, and after inserting this pair, I try to find the value mapped to the key, this should always yield the value I have just inserted. If I try to find K in a dictionary and it yields something that is different from none, this means that there is a mapping to this K in the dictionary. So if I insert some new value associated with the same K, the size of the dictionary does not change. So what I have here, I have a pair, a mapping that's already in the dictionary, and I'm updating the mapping. They should not increase the size of the dictionary, but only change the mapping. So that's the intuition of this action. And the last one, if I'm inserting a mapping that's not in the dictionary, in this case, the size of the dictionary should increase, and should increase by 1. Is that clear? So when I start processing, clicking on these buttons, it starts processing my specification. here it finishes the definition of my abstract data type. And now it comes to a place where I need to define my implementation of the dictionary using BSTs. So the first thing I do here is to define what is a binary search tree. So my binary search tree is a polymorphic type, so it's parameterized by X. And we have two constructors for this binary search tree. A constructor called bNull that will yield the empty tree. And there is another constructor called bNode that receives an element of type X, the left subtree, the right subtree, and it yields a new binary subtree. At this moment, this inductive definition, this B-tree type, is just about syntax. We don't have semantics yet. The semantics are going to be given by the implementation I provide for the functions that will come later. Do you have any questions so far? Is that fine? Okay. Here are some details. I'm saying that I wanted to try to perform type inference concerning X, so I don't want to provide explicitly the value of X. I wanted to infer the type of X when necessary. Here I repeat that the key is a natural number, value is a string, and now I say that my dictionary is going to be implemented as a binary tree of pairs of key value. So this symbol denotes the notion of Cartesian product, and key Cartesian product value yields the set of all possible pairs, and I'm saying that my binary search tree, each node is one of these possible pairs. So I have a tree of pairs. In each pair, I have a key mapped to a value. And the empty dictionary is just calling the constructor that yields an empty dictionary. Suppose, I was going to say something was not yet the time. So now it comes the implementation of the functions. So in the abstract data type, I have just the signature. So that's the place where I'm going to write the implementation of each function. So clear, basically for any dictionary, it just yields the empty dictionary. The function is empty is defined using partner matching on the dictionary. So if the dictionary is the empty one, this function yields true. Otherwise, it yields false. The function size is also defined using partner matching. So if the dictionary is an empty one, I yield 0. But if the dictionary is not empty, so it has a node, this node has a left subtree and a right subtree, and the value that I yield is 1 plus the size of the left subtree plus the size of the right subtree. Here is not the height of the tree, and then the number of elements, the size. So it's a number of nodes. The function insert is also defined using partner matching. So if the dictionary is empty, what I return is a tree with a single node, the root. The root is going to be the pair KV, and the left and right subtrees of the root are going to be empty trees. If the dictionary is not empty, I need to check whether the key is equal to the key of the root, or if it's less, or if it's greater than the value of the key associated with the root of my binary search tree. Remember that we have here a collection of nodes, and each node has a pair. So I use the function first to get the first element of the pair associated with this node. If the key is precisely the one provided as argument, the dictionary I yield preserves the left subtree, preserves the right subtree. I just update the mapping, provide a new value associated with the key K. If this was the case, if K is less than the key associated with the root, then I will run this function recursively concerning the left subtree. So I will try to insert the new mapping on the left subtree. And the third case, I will insert the mapping on the right subtree. So I'm basically traversing the tree in this very traditional manner, using a functional language to update my dictionary that is being implemented as a binary search tree. Yeah. So there is a detail here that I'm using this particular symbol. In Coq, when you write equal, it means equal of the logical way. So it's something that may be true, may be false, or may be undecidable. When I write equal and the question mark, this is the decidable implementation of the equality. That, for instance, in this case, I have natural numbers, and the equality of natural numbers is something that's decidable. So there is some syntax details here. Fine. Yeah.
So if I understood correctly, when you use the question mark, it means that you are requiring that equality to be decided too.
Yes. Actually, when I run this command locate, it locates the definition of some symbol, and this symbol is actually a syntax sugar for the function EQB. And if I print not EQB, it's going to show me how the equality of natural numbers is implemented. So there is a computational notion behind it. So something I can compute. It's this side. Okay. So find, again, partner matching. If the dictionary is empty, I yield none, so there is no mapping associated with the provided key. If the dictionary is not empty, I will basically traverse the tree recursively, trying to find the key depending on whether it's less than, greater than each node, as we typically implement. Do you have any questions so far? Suppose that now you say, okay, I have finished my implementation, so let's finish the model. If I try to run this command, that too gives me this error. You cannot finish the implementation because basically what it's saying here is that we have not proved proved that the axiom clear empty holds for this implementation of the of your dictionary. So every property that you declare in the abstract level as axioms, in your concrete implementation, you need to prove that they hold for this implementation. And you can only finish your implementation when you prove that all of these properties hold. Until then, the tool does not allow you to finish, to conclude the model that implements your dictionary. Do you want?
Yeah, you wrote axiom.
Yes, it's an axiom in the perspective of the abstract data type. So in the level of the abstract data type, I will just take this for granted. But when I create a concrete implementation of this, I need to prove that this concrete implementation satisfies these properties.
What relates them is the same name.
The same name. So now it comes the second. So this language I have shown you just now until this point is Galena, which is a functional language of Coq. And now it comes the second language that Coq also supports, that is a proof language. I have some properties that I need to prove, and Coq provides me a particular language to guide the tool to prove the properties. So now what were called as axioms before are now called theorems, because I need to prove that they hold in this particular implementation of a dictionary. I need to write again the same predicate, and now I use this keyword proof, and when I do this, it means for the tool that now you're entering on proof mode, and now the tool begins to recognize this other language, the proof language. You have here what is your proof obligation, so the objectives that you want to prove, and now you use tactics to drive the tool to prove that something that you defined is indeed true. I will cover briefly some tactics just to give you an idea of how you handle these proofs. So the first one, that's called intros, is performing universal instantiation. So before that, I had a predicate confined universally, and now I want to prove this for an arbitrary dictionary. The tactic simplify performs computation simplifies the application of the functions concerning your context. And this is done basically using partner matching. So if we see the definition of the function clear for any argument use BNew. So this term here reduces to BNew. And the function is empty applied to BNew. By partner matching, it yields true. So if I simplify this term, I get the equality that true is equal to true. And any term is equal to itself, so I can use the tactic called reflexivity to prove that something is equal to itself. And now I have no more proof goals, and I can finish this theorem. If I try to conclude my definition of dictionary, the tool is going to say, not yet, you have all the theorems that need to be proven. The next one, the proof script is precisely the same, so we just skip it. This one becomes more interesting. So here I want to prove that for any dictionary, if it's empty, D is the empty dictionary, and if the dictionary is the empty one, it's empty. You may remember that if and only if is a syntax trigger for an implication on both directions. So when I use the tactic unfold if and only if, it replaces my goal with the conjunction of both sides of the implication. When I want to prove that P and Q are true, basically I have to prove that P individually is true and Q individually is true. So now I use the tactic split, and this splits the current goal into two sub-goals, each one comprising one side of the conjunction. This symbol here is used to focus on the first sub-goal, and here I have an implication, and consider the semantics of the implication. If the antecedent is false, I know that this implication is trivially true, because false implies in anything. So what I need to do here is I need to assume that the antecedent is true, and prove that based on this hypothesis, that I can conclude that the consequence of the implication is true. In this case, I'm going to do this doing case analysis on D. So the tactic destruct performs case analysis. So this is a dictionary. A dictionary is an inductive data type, which has two constructors, B-new and B-node. So any dictionary needs to be constructed using one of these two constructors. So when I run destruct D, it creates two subgoals, considering the two possible ways of creating a dictionary. And now I proceed. Here I unfold one definition, and then I come to something that's trivial, like B-new is equal to B-new, and I can prove this using reflexivity. In the next sub-goal, I perform some simplification on my hypothesis, and then I reach something that is contradictory. I have a false hypothesis, and I can finish this proof using this tactic called inversion. So if I have false implying something, the proof is done because this is trivially true. So the tactic inversion H, which is the name of the contradictory hypothesis, concludes this sub-goal. And now I'm back to the first level, where I want to prove the other side of the implication. That is quite similar. Despite this last step, where I have in H this equality saying that B node of something is equal to B new, and there is a property of the constructors of inductive data types that says that the codomain of these constructors, they are all disjoint. So you cannot have two terms that are equal but built with different constructors. And I can use this tactic discriminate to terminate proofs when I have this in my hypothesis. And this concludes this other theorem. Do you have any questions?
You can call a proof theorem inside of another one.
Sure.
Yeah.
Sure. You can do this, you can use properties that have already been proved and are in the library of the tool. You can create proofs within proofs, so you can create kind of an anonymous proof within a proof, so yes, you can do that. This is going to, there is an example of this soon. In this other theorem, there is another tactic being employed, that's the rewrite one, and referring a previously proved theorem. So clear empty def was a theorem that we have just proven, and it says that is empty D is equal to true if and only if D is equal to empty dictionary. And now what I do is I rewrite the hypothesis H considering this theorem I have proved before, and the rewrite is performed from left to right. So what the tool does here, it looks to H, and it looks to the left-hand side of my theorem. It tries to match these with H, and if it matches, it rewrites the hypothesis, replacing the left-hand side by the right-hand side. So when I do this, I replace, and I have that D is equal to the empty dictionary. And here I have another application of rewrite, where I use H to rewrite my goal. Because if D is equal to the empty dictionary, I can replace every occurrence of D by empty dictionary. What is what I do here. And by simplification, I reach that 0 is equal to 0, which is trivial, and I can prove by reflexivity. So yes, you can refer to previously proven theorems. Are you following? Do you have any questions? So as you can see, the tool is not doing the proof by itself. Actually, you are doing the proof, but you are guiding the tool on how to do this. And the tool is checking whether the comments you are providing, whether they make sense. So for instance, if here I try to use reflexivity, it will raise an error saying you cannot use reflexivity here. So the tool is checking whether the proof makes sense. As we say, it's a proof assistant. The next theorem does not have anything new. Now there's something more interesting here. So in this case, I want to prove this other property, and this one, I need to rely on induction. So there is also support in the tool for induction reasoning. So when I do induction D, it creates two sub-goals, one for the base case and one for the induction step. And then you need to prove each one of them. And in the induction step, you have induction hypothesis. Since it's a structural induction that I'm doing here, since the tree each node has potentially the left and the right subtree, I have two induction hypotheses, one associated with each subtree. So I need to employ tactics to work on this. Here we have another interesting example where I perform destruct, but not on elements, but on expressions. So when I do destruct first x equals to k, I'm performing a case analysis on whether this expression is false or true. Remember that the equal question mark is referring to the decidable equality. So this test has only two possible returns. Or the equality is false, or the equality is true. It cannot be undecidable. And that's the reason why I can perform case analysis here. Another interesting example happens here, where if we see the proof goal, I have here some if statement where it says that k is less than k. And no number is less than itself. So I can use this previously property theorem on natural numbers to proceed with my proof. I'm not going to show here, but there is a very useful command called search, where you can search everything that has already been proven to find which previously stated theorems can help you to finish your proof. Do you have any questions? No. Okay. So here is another theorem. As you can see, the proof script comes bigger, more complicated. Here I have something like X falso, where basically replace my goal with false. I have this other tactic called apply. I don't think I should cover each tactic because it would be very low level. But what I want to show is that this tool provides you with a huge number of tactics that you need to use to show that your goals, that they are true. Let me see whether there is another interesting tactic here. I don't think so. I think that Leah appears here. Here I have something from the library. Yes, I think we are performing associative analysis here, shuffling the sum. And Leah should come soon. Here, something about associativity of the addition. Let me find Leah. Oh yes, I have used Leah here. Let me see. I think that's an interesting place. Just a moment. As you can see, in my previous script, I was invoking this particular result from the library, but I can use this tactic Leah that will encode a search that will search for relevant facts in the library and will conclude the proof for me if it's possible. So when I run here Leah, it just finishes the subproof. You can use these tactics to automate part of your proof effort. And to finish, just to give you an idea, compare. This is a script for proving this theorem. So I'm performing induction, case analysis, various case analysis. You have a lot of tactics being employed here. In this other instance of the same theorem, I have the same predicate, but I'm relying here on some tactics provided by Koch to partially automate your proof effort. So there is this tactic called auto, where it searches for the library of Koch, trying to apply previously proved the theorem that may relate it to your goal to see whether these theorems help. So since I used the debug flag, you can see here that it was trying to use some properties on multiplications on some number and sum until it found the correct theorem that solves this proof goal. This is a search, and you have some control on how the auto tactic works. So you can say the maximum number of search steps it will perform. You can define the scope of the search, so which libraries are going to be considered during the search. And depending on the configuration, the auto tactic may run in a couple of seconds, or it may take hours doing the search. So it's up to the user of the tool. So you can configure how this automation will happen. Another thing that is possible to use here is that you can use this operator, this semicolon, to employ tactics on various sub-goals at the same time. So instead of working on each sub-goal per time, you can apply tactics to all sub-goals at the same time, and then you can have smaller proof scripts. But on the other hand, they are harder to be read by a person because you don't see the very step-by-step notion of the proof that we had before. So basically, this is a single block that when I execute this, the proof is done. So you lose the step-by-step notion of the proof, but the proof script tends to be small. And since you have proven all theorems, all properties that were defined as axioms in the abstract level, you can now conclude your definition of dictionary using binary search trees. And now you are confident, to some extent, that your implementation of dictionaries using this notion satisfies the properties that you have defined. And then you can run this command, and when you run this command, actually the next one, it's going to produce a Haskell code representing your specification. And in the Haskell code, you're not going to have theorems, you're not going to have the logical part, you're just going to have the functional part. But you have now the guarantee that the functional definition satisfies the properties you define. One thing that's important to say is that when you are generating Haskell code that I'm doing in this case, note that my COP definition relied on natural numbers, Boolean numbers, strings, and so on and so forth. And I may have bugs. If I just used the string support in Haskell and Boolean numbers, natural numbers, in theory, we could have a different implementation in Haskell that may somehow compromise the properties that I proved. Because I proved the properties considering how natural numbers were defined in COC, how strings were defined in COC. So when you extract Haskell code, you can guide the translator to, if you want, that's what I done here, to extract even the code of the definition that were used from the library in COC, so that you're not relying on anything from the prelude of Haskell. But then maybe the code that was extracted is not optimized as the one of the Haskell prelude was. These are choices that need to be done. Okay. Practical application. So let me go back to the slides. Do you have any questions? Yeah.
Please. So you mentioned, that you made the choice to be faithful to what you specified when you're generating the Haskell code in terms of the data types you're going to be using. But if you wanted to use the native support for Booleans or for natural numbers and so on, are there already, I imagine there are specifications in code for them that you could show that you would be refining your specification to use those more efficient representations and then extract the code from that?
I'm not sure whether I entirely understood the question, but first, you can, when you say I'm generating the Haskell code, I can just say when I use nat, I have natural from Haskell, so it's not going to produce, not going to include in the generated code the core definition of natural numbers. So you can just rely on the prelude of Haskell. The second thing is, we have in COC formalization of the prelude of Haskell? I'm not confident to say that the whole prelude, but I would say that a lot of things that are possibly formalized in COC as well.
but you do have this sort of framework where you could show that a refinement of your specification would be one where you would use rather that definition of not instead of this one with successor and stuff. And then after you show that, you would then generate more efficient Haskell code.
But in which level the proof is going to be done?
Well, I would imagine you'd have to prove that it's a refinement to use that other version of natural numbers.
Because suppose that you have in Coq library two definitions of natural numbers. One that's a simple one and another one from Haskell. Assuming that the one that created the formalization in Coq has done this correctly, I think that for sure you can in Haskell prove that your properties hold for both definitions of natural numbers, and then when you extract the code in Haskell using the second definition, you would have more confidence. But you still have this problem that the formal definition of natural numbers from Haskell and Coq may have errors, but yes, you can do. Have I answered your question? Great. Do we have any other questions so far? No. A very interesting application of Coq, there are numerous applications, but a very interesting application is this project called DeepSpec. This project has already finished. Have you ever heard about this project, DeepSpec? So DeepSpec was a huge project funded by the National Science Foundation in the US. And they have a very ambitious focus on specifying and verifying full functional correctness of everything, basically. So it was a very big project, and there is a figure, yes, this one, it's a nice one, that makes the point. So suppose you are writing your code, and then you prove that your code is correct. When you go to the actual system, this code needs to be compiled. Maybe the compiler has an error. So what we are going to do? We are going to develop a certified compiler for C. Okay, I have proved that the compiler is correct. But what if, when my code is running, the operating system has an error? Okay, so we are going to formalize the operating system. But suppose that when you are running the code, the compiler was correct, the operating system was correct, but your hardware has a fault, and your processor executes a wrong instruction. Okay, so we formalize the hardware. So the goal of this project with a limited scope, so it's not something general proposed, so they have a limited scope. They had teams investigating the full stack of computing using Coq under the hood to formalize and prove the properties. So there was a team developing the certified compiler for C. They had a team working on a certified operating system. They had a team formalizing things like pipeline, optimization of hardware, and things like that. And they use it as a common framework, Coq, to specify and formalize this. I attended a couple of years ago a summer school organized by this project, and there was a talk, interesting talk by some researcher from Intel, and he said that they found, they could not say what was the processor for obvious reasons, but they found a very, very rare situation where the processor executed a completely random instruction, despite of what you have asked the processor to execute. So I remember that there was a famous researcher in this area that his goal was to formalize and reason talk about the C library for manipulating memory allocation. So formalizing the malloc behavior, formalizing the free behavior, and things like that. And another interesting result of this project is this series of books called Software Foundations, where they provide a very comprehensive presentation of COC and how you can use it in very different levels. So the first volume, which is called Logical Foundations, presents the basics of COC, but it goes until, for instance, a tool called Verify the Software Toolchain, and what this tool is capable of is you write C code, for instance, using linked lists, and then the tool converts your C code to a COC representation of the C code. So now you have precise semantics for this C code in COC, and then you can in COC reason about the correctness of your C code. So there are very interesting results on these books. So there is another book focused on algorithms. So that was the inspiration for this example. Here they address a more complicated example where they prove the correctness of maps, but there's a first step using binary search trees, but it's slightly different. But then it uses red-black trees, which is a more interesting implementation of dictionaries since you have balanced binary search trees. So that's another interesting application of COC. And to conclude this part,
I have a question.
Yes.
You said it extracts specifications, right?
Yes.
It includes also properties to be verified or not?
I have never used the Verify Software Toolchain in great details. Mm-hmm. So I don't know whether when you, for instance, you have in your C code a malloc, when it produces the COP code, where they automatically include the properties you need to prove to guarantee that your code is correct, or whether you need to write by yourself all the properties. Was that your question?
Yes, because I thought it might be interesting to generate all sorts of properties that could be extracted and proved on the specification as well. You know, some kind of AI application for that.
If I'm not wrong, I think there is you know that when you're reasoning about programs, something that's hard is when you're reasoning about loops, because you need to provide a loop invariant to prove the properties. I think there are some work going on to integrate artificial intelligence applications to try to figure out automatically what are the loop invariants. Because one thing that's not, when they're using these tools, not the VST, but there's another book that I have used in teaching, and when you want to prove the correctness of some classical algorithms, the hardest part is not doing the proof, but figuring out the correct loop invariant. So there is some research going on this idea of using AI to deliver automatically what would be the invariants.
Okay, thanks.
Sure. So what I was going to say before, some years ago, I don't know, maybe 7 years ago, there was an email on the COP list that became very popular because it was a company in Sydney, Australia, trying to hire people to work on some practical applications of COC. And what was distinguishing in the call is because they started saying what was the scope of the work. They said that you should have some background in C programming, and then it said something like this. We also expected to have a good background in logics, a good background in discrete mathematics, and then it said, if you have ever used tools like COC, Isabel, PVS, please apply to this call. We are going to buy the flight tickets, we are going to give you money to rent some place here. Basically, we move you from any place within the world to Sydney to work with us, because it's not very easy to find people with this kind of background. And the summary is, there are real applications of this. Okay, so let's see. Yeah. So to conclude, I hope that you are now more familiar with this area of formal methods, where the main goal is to provide mathematical approaches to support the rigorous specification, design, and verification of computer systems in general. There are many tools, many languages covering different aspects. Like we saw, there are languages for addressing single-thread systems with no concurrence, with no time properties. There are languages focused on concurrency. There are languages focused on time properties. I have not addressed it here, but we also have tools for addressing probabilistic properties. So there is also tools on these. There are tools for discrete systems, tools for continuous systems, tools for hybrid systems. So there are a huge number of initiatives in this area. And to conclude, if you want to read more about this, to get some more in-depth overview of the area, I suggest these two papers. The first one is a survey of professionals both from Europe and North America on how they use formal methods for developing dependable systems. And the second one is a survey from people both from industry and academia on the research and use of formal methods. And this survey, they also had some Turing Awards recipients answering the survey. So there are also very nice insights on this second paper. And there are some books, each language that I mentioned, B, CSP, COC, each one has book or books, but general books with a more general overview of formal methods. There is this concise guide, formal methods, and there is also another interesting book on rigorous software development. So these are my recommendations for reading about this subject. So thank you very much once again. Thank you, Daniel Adija, for the opportunity. It was really nice to be here talking about formal methods for you. I hope you enjoyed.
PhD, I came back to Manaus, so I started as a professor at the University of Federal University of engaging with both postgraduate programs, the one in electrical engineering and also the one in informatics. And then after 5 years here, so then I was missing the UK weather, the UK food. So then I decided to go back to the UK. So as a postdoc in the computer science department, under the supervision of Professor Daniel Kruning. So I spent 2 years working as a postdoc. And that, so lecture, which is equivalent to a professor in the Department of Computer Science in Manchester. And then in 2021, I was promoted to reader. And when I was promoted to reader in program analysis and cybersecurity, create a group. So our department of computer science is around 80, 85. Science department groups. And then we have around 10, 11 groups, okay? In this Nado Magri, just here, from São Paulo. Also another colleague that originally a British company that they develop processors, and so Center of Excellence of the top universities in the UK, and they give funding for PhD studentships. So it means that every year we get funding from Army to develop PhD theses related to the research of their interest. In this case here, so we have three main categories. I don't know why it's quite, I don't think that you can see well here, but then advanced process technology, that's more people from hardware, then machine learning and robotics, and they decided in 2021 to introduce systems and software security, and that's why I became the director of that Center of Excellence. So that's a bit of my history, right? If you have questions, please raise your hand and then ask your question, okay? I told Edja that the talk here today is going to be a bit of massive research, right? So you might lose the focus here as you go deeper, right? But yeah, feel free to ask questions. And if you can ask in English, you can ask in Portuguese, okay? But the important thing is that you try to ask questions, then you try to interact here, because it's going to be the entire afternoon, and then you're going to sleep if I'm just speaking here to you, okay? Good. And the last one here, I also spent 4 years to build here, help my colleagues to build this research center, Digital Trust in Society. And in particular, I have created in those 4 years, one cluster that's called the Digital Trust. And we have colleagues here that work in different domains, not only computer science, because nowadays when you talk about cybersecurity, at least from the UK perspective, so they want to see people from social science, people from law, people from math, computer science. So then this research center here, we have colleagues from several different departments in schools that we get together to work on that domain of cybersecurity. Okay, good. So that's a brief overview about myself. Now let me, I don't think that's good, right, the quality. Is there some way, guys, that we can improve this visualization here of the slides? No? Sorry. Porque tá meio embaçado, né? Você consegue... Não, é o projetor mesmo, ok. Se você quiser em diante, beleza. Okay, good. So I think here this slide is the main motivation here for this talk. So we have already motivation, right, about to develop safe and secure software systems, how formal methods can help, right, to achieve that goal. And so this is a report from 2022 that I like very much. It was a survey that was made with several companies in the US, right, to study about, software development process, the case that they succeed, case that they fail, okay? And so then they have an estimation here on this survey about the poor software quality in the US, in the range here of trillions of US dollars. And then we have this diagram that you can see very well, okay? But then here in this diagram, so you have a big chunk that is related to find software vulnerabilities and also fix those vulnerabilities. It's about $800 billion, right? And then there's a lot of motivation in this report for researchers to develop methods, algorithms, techniques, tools that can help software developers to find bugs and then fix those bugs, okay? And in this talk today, so I'm gonna show you, I will start describing the logic-based automated reason framework that we develop as part of our group, how you can reason about the safety, security of software systems, and with the success of the large language models, right, from as you have at the end of last year. So early this year, investing quite some effort in our research group to integrate large language models to help us repair software vulnerabilities, right? So Haniel collaborates with a great guy that's Clark Barrett. And Clark Barrett, for example, he sees large language models that he can help in other directions as well, for example, to help in program verification, even use SBMC to get if LLM, use LLM to produce invariants, as Gustavo presented here, and then use SBMC to check whether those invariants hold, right? And then he can show that, well, with the invariants that he extracts from large language models, he can verify more programs with SBMC. That's the platform that we're going to show here, okay? So then the focus of the talk is going to be methods, algorithms, and tools that you can use to find vulnerabilities and fix those vulnerabilities, right, in software systems. So that's an overview. So I have been working on this field since 2000 as part of my PhD. The first paper that I published about this work was in 2009 at ASE, the Automated Software Engineering Conference, which is an A-star conference in the field. And this year, like 12 years later, 13 years later, so that work was recognized as the most influential paper at ASE. So I was in Luxembourg in August to receive that award of this work. So I'm going to show you a bit how was the journey, right? That when you start the SBMC and then what I've done in this field over the last 15 years. Okay, so then it includes here. I'm going to give the overview of the reason platform to the software. Then I'm going to show how you can use this platform to do software testing, software verification, and software repair. And then I'm going to present here to you also our view, right? Next, right? And in particular, we are developing here a high approach that you can do hardware software security, the combination of those two fields, with a particular focus to check properties related to memory, safety, and concurrency. Okay? Questions so far? No? Good, so let's start here with two research questions, right? So we know that overall, program verification is undecidable, right? So given an arbitrary program with an arbitrary input, we cannot determine whether, right, even property is going to hold or not, right? That goes back to the proof that was made in the 40s by Alan Turing about the halting problem, right? And a lot of work has been done in the field for people to push the state of the art, right? So developing better data structures, better algorithms that can help us to prove the safety and security of software systems. And then here in this session today, so I'm going to show you how you typically cope with that kind of problem. And also, if you take a look at the field, so that's a very important field in software engineering, formal methods. So formal methods is a subfield of software engineering. I don't know if people can disagree here, right? But I see it as a subfield of software engineering. And so, as I have shown to you in the report, people are quite interested, right, to find and fix vulnerabilities. And then there are lots of research groups that work in this field. And then, well, what do you do in special that you can find more vulnerabilities than other existing approaches. And also, if you can automate, right, the process to find those vulnerabilities and how you compare with the state of the art. There are two things that I like very much in my career. So the first is I like very much participating in competitions. I think Raniel also loves competitions, right? The competitions, they allow us always to get better. Every year, you try to design a better data structure, a better algorithm, and prove more and more safety, security properties in programs, right? So I have participated in all editions of the software verification competition, software testing competitions, and I can tell you that it helps quite a lot our research to engage in these competitions. And the second point that I like very much, interaction with the industrial sector. So we're going to see here throughout my presentation that we have a lot of collaboration with the industry. So we have Gustavo mentioned about Infer at Meta, right? We have here the platform that I'm going to show to you is used in production by Intel. So Intel, they have firmware written in low-level C code, very close to the hardware. And so they use this platform here, right, to verify. In particular, it's integrated, as Gustavo also pointed out in Meta, in the continuous integration environment. Every time that the so they a commit does not break anything. And that they work in the firmware development from traditional software development is that they have specifications, right? Talking quite a lot about specifications today morning. And so then the specifications in natural language, and then the engineers, they get this specification natural language, and then they write assertions, logical assertions, right, in the code. And those logical assertions, they define and post conditions of those logical assertions, right? And then they use a verification engine like this to discharge, right, those verification conditions, and then check whether they hold or not. Okay? So Intel is one case that used in production. Another case is ARM. So I had one of my PhD students, as I told you, have the Center of Excellence in ARM. And so he has also introduced this platform in production. And it was quite interesting because also they were at Army, and then you had to show that, well, with our technology, we could verify properties. I mean, I could either find more bugs, right, or prove the safety, right? Positive. So I'm not going to show that outcome here. We are just working right now on a research paper to try to submit to CAF early next year. So let's see if it. Yeah, that's quite close to the deadline, right? And yeah, so that's the two things that I like very much. That's the competition and industrial partnership, because we learn quite a lot when you try to when you design our algorithms and then try to apply those algorithms. So then we get a lot of feedback from people that work in the industry, and then see ways that you can improve scalability, can improve usability, right? Because I think these are the two main issues when you talk about formal methods, right? That you want to solve scalability, you want to verify even large systems, right? And then it should be easy to use. I think that the developers, they usually give feedback for us about this technology here, is that when you find a violation of a property, we provide a counterexample. So I've mentioned, right, about the counterexample. So the counterexample is going to case that I can go from the main entry point of the property, we can violate, refute that property. And sometimes the counterexample is huge, many thousands of lines. And then it becomes quite hard for the engineers, right, to debug and then try to understand where the vulnerability is. And that's something open in our group, that to try to develop tools that can help them as well to visualize, right, those traces in the code. Good. So yeah, the quality of the slides are good, okay? But here the data show that does not help much. So this is the platform that I'm gonna introduce to you today here, okay? I can split into three parts. We have the front end, the middle end, and the back end. Guys, if I use Microsoft or Zoom, I think you might get a beta. Do you have Zoom? No? Because I think it's quite bad that people can see. Yeah. Okay, so then the front end, I think there are two important decisions that I have made here with the group, this platform. So the first design decision was the following. I said, look, we are not going to be compilers, right? So we're going to use compilers of, and then when you use compilers off the shelf, we essentially extract syntax tree. And then all compilers here that you consider in our framework, so you always get the AST to translate data representation. That was the first design decision here for this platform. And the second one, we want to make the platform quite modular, right? And then one of the the most difficult part here of the problems that you try to solve, actually, there is the research Haniel that actually tries to solve the problem that you produce here. SMT backend, automated theorem improvers. And so in the end of our platform here, so we can connect any automated theorem improver, right, that can understand the SMT-lib. So Gustavo again, so it was a great talk from Gustavo. So he made my life much easier now in the afternoon, right? So if the automated theorem improver, they understand the SMT-lib, right, so then we can plug in this platform. And then we can plug in two ways, either via a native API, okay, and the entire platform is written in C++, or you can just output a file with a logical formula and then give it to the solver, right? And then we can parse the output and so on. And we have here a bunch of SMT solvers that Bulecto, Bitwoodsla, EISys, MFSAT, CVC. And for example, and why they develop their own SMT solver, I don't know, but they have their own SMT solver, right? And when they don't want to use the Bulecto and Z3, the other two SMT solver that they use. As far as I know, they don't use CVC5. Platform here. So assume, asserts, start, thread, which is very close. Also, they made the representation, then lots of things happen here. You have the code. So then we can division arithmetic overflow. Knows this FG operation, right? That you can check for undefined behavior. So we add labels to the basic blocks of this FG, right? With two goals. One, I want to produce test cases, right, to improve code coverage, and also produce test cases that you can find vulnerabilities in programs. Okay, and remember here, this technology, here's a push button technology, right? So keep the code, and then we do all the work for you. Okay. After the code instrumentation, then is here that abstract. Yep. When we symbolically to and from memory. Then you consider things like a little big, right? So then we started here. When you see program, going to show the safety of. And also when you do this, then you have try also to simplify further, right? The formula that we do program slicing, right? Given the property, you are gonna consider the assignments that are related to that property that are gonna check. So you remove. They do a good job writing these kind of things. They say, yeah, but we can still help the assembly source doing this in the level of the program, right? To remove those unrelated assignments. And then there's also caching, right? In any particular case here, so you do a cache in the level of the SSA, the static single assign form that I'm going to show a bit later how it looks like, right? Of the verification condition that's produced, because when you unfold the program, there's a lot of repetition, right? And then you can cache those VCCs here, and then also help the entire verification engine when you try to verify a given program. And then the output, so yeah, Daniel. The pieces don't here.
So usually our
There's also another member from my group, Eduardo. So that's the guy from verification of neural networks. Nowadays, AI is everywhere, right? So that's the guy that's trying to verify AI models.
So the question was how the caching system in SBMC works. So basically, each VCC, which is a verification condition, consists in a set of steps that must happen, which that implies a port, the assertion, the property that must be met. This is easier in SBMC because internally these expressions we have our own way of dealing with expressions, intermediate representation expressions, and we calculate it based on a SHA-256 taken, and it's basically a sequence bottom order set of them, and then at each interaction of corresponded, So at K1, we look in storage which is currently verified. At K2, we look if it is still on the set. If it is, then different.
And it's quite efficient, you know, in practice, if you verify firmware, it makes a difference. The firmware, they have a lot of bounded loops, and there's a lot of repetition. Yeah.
What's the difference between either and compiler's error? Because it's quite similar to each other.
Code. Yeah, there's a lot. Yeah, as I told you, right? So I want to put a focus on verification, right? But there's quite a big overlap, right, with compilers. The difference here is that reason about the safety and security of a program. Then when the reasons like get the program, and then in that program, we are gonna explore, right, the entire state space of the system, right? When you talk about the what space of the system, right? So the mathematical formalism that we use here is a transition system. Transition system, we have the initial states, a set of states, how I can move. Do the verification here, so you build a transition system that are going to explore. For example, my input that I have for my program, the no determinism, right? For example, let me say that I have a variable A, and then that variable A is going to be given by the user, okay? And so then you don't know. If it's an integer, it be any integer, right? And let me say that you have an assertion that's going to check the value of A. And then with the verification engine here, so we can assign a no determinism to the variable, then explore simply the entire state in order to tell you whether the assertion is going to hold or not, right?
So it's code from the code that was in
it is the original code, but then lots of transformations, right? In order to claim whether the assertion is going to hold or not, right? And then the case here of compiler, so you don't have that ability to reason, right? You don't have the ability.
It's not like a compiler. It's literally change the code to make it better and more. I still don't understand what safety means. The code. Sorry.
Okay. No, that's fine. So I'm gonna have examples in my slides going further here. But imagine the following. So let me say that we have you declare an array A of 5 positions. And let me say that I have a variable I, right? That's going to have a pen here that I can know, right? Yeah, maybe I could use the... And then you have it has with 5 elements, right? C plus, right? For example, then it goes here. We start at 0, right? To index the array up to 4. And let me say that, well, that, good. Yeah. Yeah, let me declare here each A 5, right? And then, well, we have some code here that are going to manipulate that array, right? And then we have a variable here to index the array, right? And then that variable I here is an integer, right? One example of safety check is check whether is data 0 and I is smaller than 5. That's a safety check. All right, so when I'm gonna statement here, so I'm gonna theory of arrays, this over, right? That is select the range of I, and I should in that interval is that interval weaknesses enumeration, right? That's our web in software. is buffer overflow. Good? I will not allow you to do that.
It's not compilation. I was thinking that.
No, that's good. Good question.
Okay, thank you.
Good question. No? Good. So let's move forward here. So then the output here, we have two possible outputs, right? Either the property holds, and if the property holds, we provide invariants that we explain it today morning. So the invariants, what they are? They're conditions, right? Some predicate, right? About something that's true about the program, right? In a particular location. And then with those invariants, they're going to tell why the property, right? Why the program is safe. And in community, they use a specific format for the witness, right? Because there is another field of research that people are going to check whether that correctness witness here, right? Whether the invariants that you produce, they're going to hold. Or if there's a property violation, right? We provide a trace. And there are also witness checkers that are going to check whether that trace, that counterexample is a real counterexample, purest counterexample. Okay? So, and then the case here, when you find a property violation, right? So then you provide a trace. And then as I told you, I'm going to show a bit of the research that I'm doing here, integrating large language models to repair the program based on a verification engine. In this case, here we provide the original code together with the counterexample, right? And then the large language model is trying to propose a patch. And then that, right? I'm going to show you later. It happens also, it does not matter if it's AI or if it's human, right? So even human, when they try to fix a bug in the program, sometimes they can fix, but sometimes they can introduce new bugs, right? And large language models are going to do the same. And you have the patch, you have to use the verification engine, whether patch is going to fix the vulnerability. And the results are quite fresh. I'm going to present here to you. I have one PhD student work on this topic. We created a large data set based on LLM, more than 100,000. Then we good questions about the architecture? Yeah.
In your middle end, if I understood correctly, you have some sort of transition representation.
Yeah. It's a transition system.
Yes. My question is, this representation is for each one to check.
In that intermediate representation that you have here, so if it's a C++ or C, right? Python. So you can see here, I don't know, nowadays the computer science students, they love Python, right? And then you don't care anymore when you reach that stage. And then you can apply all those algorithms that you don't care much about which program language, right? Because here, in the symbol, we have encoded properties that we want to check, okay? And when you produce those, so it varies also from program language, right? In the case for C and C++, you know, that's an unsafe program language, so they tend to produce lots of safety checks, right? Here. And then there's a lot of research in our group, for example, in the case here of Solidity, that try to understand the common vulnerabilities that you can find in smart chain, right? And we use knowledge here, right, in the to create those safety checks, right? And then the research here, as you can see, support new programming language, support new types of checks for vulnerabilities, right? Cope with the state space explosion problem, because our main problem here is going to be scalability, right? Gustavo has mentioned also a bit about this, right? Because we try to represent, right, the entire state space and then explore the entire state space sometimes can be huge, right? Also, other things that I consider here when you try to build such a framework, there are two main items here. One is that, okay, so you do the search, as usual, as you can see here with all constraint programming, SMT solving, etc. But we're also looking at some way to integrate machine learning, as I mentioned with Clark Barrett that works with Haniel. So he producing variants from LLM to help, right, the verification engine to solve more and more cases, right? I've also to explore parallelization, right? So that's something in our field, right? Even the SMT solver, so Haniel can speak better, right? So we have put a lot of effort to make those architectures that can run in parallel hardware, right? In multiple cores, different machines that start communication. In the SAT competition, so we started seeing SAT solvers, right? Parallel SAT solvers, they consistently outperform sequential SAT solvers. And then parallelization is crucial. And then the last one is memory, right? So, for example, the case of caching is one example of memory. So you have to explore, right? Search, learning, parallelization, right? And memory, so that you can try to scale. Okay? Good. Yeah, and then, yeah. Yeah, it's getting. Rafael, how many lines of code do you have? But I would say at least 500,000 C++ code. 300,000. Yeah, as I told you, the hardest part is the backend, right? Yeah. We have around 500,000 lines of C++ code. And here, in this front end, so the C and C++ front end here, they were used in production, right? I told you Intel, Army. We also had Nokia in the past that they have used the C++ extension here of SBMC. Solidity is a company in Hong Kong. So we publish, that's quite interesting. So something that you guys have to keep always in mind is to publish in top venues, okay? And the top venues, they give visibility to you in your work. And for example, in this case of Solidity, we managed to get a paper at ICSI, which is the premier conference, right, in our area. And our company said, oh, I like it, your approach. Can you extend this further? And then I give you a fully funded PhD scholarship to work on this. So then I have Shefeng that is work on that topic. And also another example here is the Python. So that was the Ethereum Foundation. So the Ethereum is when you apply for the grant, and then they allocated some funding for us to develop this Python front end so that they can test the Ethereum, the specification that they write in blockchain, which they use Python to write the specification, right? And to make our life easier, so they usually annotate the type of the variables in the specification. And then it also helps us quite a lot, right, when they annotate the type. Because here, we are a bit precise verification engine, okay? And then it means that, well, we're going to consider the bit width of the variables that we have in the program. But you can say, Lucas, yeah, but Python you also have unbounded integers. Yeah, that's something that I now adding support to the platform. Also deal with, right now, the entire platform is precise. Yeah, and that's something that we're also expanding with this industrial that I in the beginning, right? Industrial part, they push us to make things better here. Daniel.
I was just a bit surprised because generally it's going bit precise, that's harder.
Yeah. But we didn't have any support for unbounded integers. Some spec from Ethereum, they use unbounded integers, right? Yeah. Good. Questions here? No? I think that's a general overview, right? Well, try to write some PG. Good. Structure here four, right? So that's I'm gonna give quite easy introduction here about general BMC architectures. Our platform here. Then show a bit of the software verification test that you do with this framework. Here, I'll show, again, it's a collaboration with an industrial partner from UAE. That's called Technology Innovation Institute, where they are using this verification platform to automatically repair code, right? So then we also have a PhD student involved in this collaboration. And then the last part here is future work, right? How you can see that field of verification exploring hardware and software security. That's security. A new 100% and then they that right, so ele já told me that I can go until 6 p.m. Right? Good. Yeah, everything starts here. Field of so breakthrough started in the 1993. The CDCL, the conflict-driven cloud learning solvers, then doing with propagation and so on, and in the solvers that they could check formulas of constraints, right? And then you can start seeing applications of program verification, program testing, software synthesis, and so far, right? So I think there is a talk from Armin Beatty that he announced that a talk 30 years of such solvers, right? How they can make it faster and faster. So for me, from formal methods, software engineer, so that's the key technology, such solving. Okay, that's the core. And as I told you, there's an annual competition in such solving. And in the last, as I mentioned, the last 2-3 years, parallel such solvers consistently outperform sequential such solvers. So it means that you can verify even larger programs now, right? If you explore the parallelization part. And the other part of the key technology here of our framework is model checking. Good that Gustavo introduced a bit of model checking, and he also mentioned a bit of BMC, right, about model checking in his talk. The basic idea here of the model check, as you have learned with Gustavo, is that, well, we're going to build a transition system, right? And then we're going to have a property, and then we're going to check whether that property is going to hold, right, in my transition system. That transition system can be a hard or synchronous or asynchronous transition system. And if the property holds, the device is going to give you a counterexample. We know, right, that model checking is not very good to find bugs, right? And then I can tell you from the practical application of this technology, right? So it's very, very good in finding bugs. And questions? No. Then I'll have an extension here, right? What's the research that overall program verification is, right? So one way to achieve here decidability, right, is that, well, we can bound, so we can have some techniques here that, well, if there's just fine T to show explore all possible states of your program. And it means that here is threshold, right? This threshold is going to tell you whether unfolded the not so and then they produce. You need unfolding etc. Computing the complexity threshold. Why we find bugs. And the colleagues who invented model checking was work with him together. I did a consultancy for a company, and we worked with the consultants that no typical about model checking architecture. So I would right select learning. That was the guy who developed it. About model checker that you could apply this to software, in this case for C programs. Then later they also use it for hardware verification with Verilog. They base it on site solving, right? Even Daniel visited me like 3 months ago in Manchester. And then I made a joke for Daniel. Hey, Daniel, CBM with the last commit, right? Also had a content as from CBMC, right, as part of my PhD. So I started work at CBMC, and then during my PhD, I have diverged I have some diversity. Daniel, right? So Daniel used to like develop everything by himself, right? The front, middle end, excuse me inside. Apart from that, develop everything by his group. I said, look, at the beginning, I have the design decisions. I don't want to develop. I'm not going to develop an approach, right? Focus on verification. And that's the first work I received was assessment and I had Sean say, then you had a device. I said, but if you believe it's quite slow, you should, which is faster. Memory, right? Transformation, so on. No, it's not going to be okay. Then let's talk. That's the right, if this platform here, that I'm going to show this work, that in 2011, or 2011, we published at ICSI, paper one at ICSI, which is the and then just a very important dynamic programs that here memory model. See the determinism of the interleavings. Right? So just interleavings here, right? For you to have an idea why it makes our life much easier. Para pagar aqui a não? Eu vou usar aqui. Instruction 1, A2, B2. 2 threads, instructions, each thread. Quite simple, right? It does not look that simple because if you consider here, when you do verification of concurrent models, so we have the system and memory, and then let's start with the sequential. Read while you write. In this case here that I have just 2 statements, so I have to execute first A1, execute P1. and then B2, okay? And execute A1 and A2. I can execute A1, B2. If I have executed A1 to B1, then it's gonna be B2, and then here it's gonna be B1. I start with thread 1. And what about if I start with thread 2? You do the same thing here, right? So I have A2, and then either execute A1, or I'm gonna execute here B2. If I have executed A2 and B2, then it's gonna be A1 and B1. And then here is gonna be either B1 or B2, right? And then here's B2, and then here B1. And executions here, I have 1, 2, 3, 4, 5, 6. Very simple program, right? And as I mentioned, so include the node determinism of data and the node determinism of the interleavings. There's a lot of research. So my PhD, right, was in that area of verification of concurrent programs. And there's a lot of research for us to cope with the state space exploration. Right? For example, techniques here like partial water reduction, that to check the transitions and then see whether those transitions are redundant, and then you can remove them. Or do caching, right, of the states as well. So there are ways that you can improve here the exploration of those concurrent programs, okay? So in this case here, those model checkers, they support concurrency, right? A lot of BMC is just for sequential programs. They don't do concurrent programs, right? But CBMC does. Yeah.
It should be like, say, the execution of A1 for the two. That would be.
You're going to start producing states, right? And then you put those states in a hash table, right? And then when you produce a state, you're going to, it's quite to just the hash table, right? And say, oh, did I produce already that state? If I've already produced it, right? So then I'm done. If I use state, so then I produce a state and then add to the hashing. It improves a bit the performance of the verification doing that hashing.
You can also verify the part.
Yeah. We can also encode, right, those, I mean, you can either do here an individual, what you call exploration, right? Or you can encode all those interleavings in one single formula, right? From our experience, depending on the program, right? So, the main bottleneck that you can get when you encode all interleavings in one single form is that sometimes the solver can explode. And then if you do individual exploration, because it's lazy, right? So the formula is much simpler to the solver. And yeah, there are different strategies, right, that you have to explore. Good? Yeah. Nice. Now come the safety checks. I have shown to you here the buffer overflow, right? But as you can see here, well, you can do overflow. It can do leaks. When you deal with employees, right, that use malloc, right, and blah, blah, blah. Deadlocks, when one thread waits for the other, right? Race conditions. All those properties that the safe checks that you can see here can produce those safe checks automatically. And they also, CBMC also, they do most of them. They don't do deadlocks in CBMC. I don't think that they do race. But there are all the model checkers that they can cope with that. So you can also add user assertion. As I told you, Intel, they get a specification of what the firmware should do, and they write, right? Also, they have labels because you want to produce tests, right? And from the industrial perspective, people very much testing, right? So then when you develop solutions that automatically use test case for developers, love it because you know that they spend to write the test. Okay. And then the node determinism modeling here that you can use node determinism assignment, right? So for all program variables that you have in the program, so then you can introduce node determinism, right? And also restrict the search space via assume statements. I'm gonna also show how you can use node determinism of the program. Okay, good. I have shown to you a very complicated architecture. Not very complicated, but with many modules, right? But the core is like this. You have the program, right? Here I have made an instance quite simple, get a C program here. Then you have the parser, get the intermediate representation. Then do static analysis, right? To do all types of code instrumentation, transformation, and so on. And then you produce logical equations using either propositional logic. You can use a fragment of decidable, the first order theories that you have, right? In this case here, I have just focused on a simple case that, well, let's do propositional, right? And then we build here the CNF, have the CNF generation, the conjunctive normal form, right? And then with the CNF, so then we give to the SAT solver, right? They're gonna say, well, if there is a property violation, you get a counterexample. Otherwise, it's gonna give an output as safe, and then say that's unsat. And they also provide information right here with the core why the formula unsat. And as I told you, so here's another field of research, right? That I don't go deeper here. Maybe it can be a next for Haniel, right? Go further here with you, right? So I'm more a user of this technology here. Good questions? No? Yeah, then this is the general approach. We're gonna get here, do the simplified control flow. We're gonna go step by step here with you. Then we unwind all the loops that you have in the program. Then we convert what we call a single static assigning form. That comes from compiler domain, that the colleague here is quite interested. And the common property in SSA is that for every assignment that you have in the program, right? So you have the variable, and every time we do an assignment to that variable, we keep the original name. Then I'm going to show examples as well. Then we convert to logical equations, try to simplify. And as a last resort, we bit blast. What's the bit blast? So produce here with true and false, right? And then the SAT solver is going to check whether the form is satisfiable. And if it's satisfiable, then we convert the SAT assignment to example that can be produced for a test case, or we can give this other large language model to produce a patch to the program, right, that we're going to do here. And that's very nice here, right? So for those that work on learning, right, so you talk about about explainability. Yeah, model check coming from the context example. When you find a problem here, we can tell you how and reproduce code. The value I have to assign here and then go through the code to use the bug. Good. Flow simplification. So you can get expressions like, okay, I have j plus I, so then it becomes something like I with I plus 1 and j equal to I. Why you do this kind of simplification? Because it makes our life much easier, right? Later, when you symbolically execute the program. So you try to simplify, right? And then we also we replace for, while, do while, right? And then just use go to, right? Go to expressions, if expressions, right? I'm gonna show also examples how it works here. And makes, again, our life much easier, right? Because at the end, we just see go to expression. And then, then also make the control flow explicit, right? Replace continue break by go to. and then replace the if while by go2 here. So let's see the example. I don't know if you can see well from here, right? But then you have the program, int ij, and then you have the loop for, I equal to 0, and then I is smaller than 6, and then I plus plus. And j assign i's, and assert j equal to I. And from this representation here, as you can see this transformation, right? So we have converted here the for to while, and then from while to go to program. Right, so you have I and j, then the initialization of the for, it's here, and then look, here, I is smaller than 6, and then you negate, and then if the condition holds, then you gonna check the assert, or the device are gonna execute the statements inside the loop. And as I told you, why you do this? It makes our life much easier to symbolically execute the program, right? I also get lots of questions. You took the design decision and byte code, because I know the compiler, Clang, code, right? And lots of transformations in the byte code. But in our case, we work on the AST level, syntax tree, right? And then you use the go-to representation. Because that language, when you symbolic execute to produce SSA, that's going to be a language that's going to be quite easy to translate to the background theories of the SMT solvers. And okay, look, it is okay, but what about performance? Yeah, I want to show a comparison paper that can show that, well, with to model to verify based on the byte code for much better. There's a lot of code, and then here a lot. Yeah. Don't have done didn't work. Try, right? Common sentence. Somebody I don't remember now that failure is success in progression. Right? So you fail, but you learn, improve. You learn, improve. One time. Good. Yeah, then here's the SSA representation, which for those that are familiar with the background theories of SMT solvers, that's quite easy, right? To encode the SMT. Right, have the assignments. We have here the relational operators. We have the ITE operators. It maps almost one-to-one. And as I told you, we can plug, it's modular, we can plug many SMT solvers here. But there are things that, well, not all solvers they support. For example, Haniel was asking me, well, you guys have a floating point layer that they understand the IEEE 754, right? Not all SMT solvers, they can cope with the floating point theory. In all programs, they have floating point, right? Now Eduardo doing verification of neural nets, so if you are here tomorrow, please come to the talk of Eduardo. He's going to show you lots of examples of floating point in neural nets, right? They don't understand, some of those SMT solvers, they don't understand the floating point theory. And then you had to develop a layer in SPMC that we understand that representation, and we produce bit vectors, right? Which all SMT solvers they can cope with. Another layer that you have here also is about tuple. Not tuple. Structs. Pointers. Oh, Lucas, you model pointers with tuples, yes, with two fields, the object and the offset. Quite simple. But no, not all SMT solvers they support tuples, and then you have to provide that layer, and then again you provide the bit. I think Z3, right, Rafael? Z3 supports. Yeah, sure. It support. Yeah, at least my PhD email that I use the type. Good. Questions so far? Fine. Okay, let's move forward. So then there's the loop unwind. Then the loop unwind. So you are gonna have here an example. Let me go here for the example to show you. So we have the function here, and then you have the loop. Okay, why the condition body? And what the loop unwind? What we're gonna do is essentially you are gonna here. And then every time that we unfold the loop, we put the body and then check whether the condition holds, right? Because if you unwind the loop, you start unwinding, right? So then you're gonna be a set of unwindings that you have here, right? And then the last one is gonna be what you call, that's quite important here, unwinding assertion. Assertion. So you want to have formal guarantees. You can see it's going it's the while just with go to here, right? And then put the assert at the end to check whether it has unfolded enough. And Lucas, can you do always, it's configurable, yeah. You can configure the platform to add those that assertions. Or you can also, example, is unsigned, right? We introduce here the idea of a partial. So with the partial loops, we can actually, how many times we can unfold each loop, and then don't consider, right, the unwind assertion, and then just unfold those loops, and then let's see what happens with the correctness of some assertion. But that approach is unsound, is available in the platform, right? If you want, let me say, I want to unfold 2 times this loop, 3 times this loop, right? And then check the assertion. You can do it, okay? But it's unsound, right? Because the idea is that we'll have to unfold enough that loop, then go to the next, right? And so on. But some of our industrial partners that they sometimes find some interesting to see some part of the code is reachable, blah, 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 right? So then we have this option available as well in the platform. Good. Yeah, then the example of the safety conditions, right, that I have shown here to you. I don't need to go here again, so let me skip here. And so then point out here for you that I have shown about the intermediate program, right, how you produce. And then comes the part of the equations, right, that we consider here the safety conditions, right, that we want to verify in the program. And then I also show you here quickly how, when you build those logical equations, right, how the solver can, especially such solvers, right, and then the generation of SBMF here, which kind of algorithms you can use to perform that, right? So then let's get here. So let's transform here a straight line program into. So then I have this very simple program, x0, y is equal to x plus 1. Then z is y minus 1, right? And then, well, when I'm going to build the equation here, see, then I'm going to get here x 0 and y x plus 1 and z. And then here, these assignments as the constraints. Okay. We build a PMC approach. We build 2 sets of formulas. One, that's the assignments, are those constraints, and the other one's about the properties that we want to check, okay? Then let me say now that, well, we have a variable. The same variable is assigned multiple times. Comes now the concept of SSA, a static single assigning form. Then x equal to 0, x 0, assign 0. Then I have x assigned x plus 1. x1 is equal to x 0 plus 1, right? And then x assigned x minus 1. I'm going to have x2 1 minus 1, right? Every time that I assign a value to the verb, I keep the original name and then I create the index. And as I told, that's the language that the SAT solvers they understand, is the SSA. That's crucial here, okay? Now, Lucas, what happens if you have if and else, right? So we're gonna have here x0, y0, then x1, z0, right? And then y is gonna get x. y1 is gonna get what now? And then we use from compilers, if you remember, right? Although you don't do research compiler, but as you have realized, there's a lot of overlap with compilers. So then you use here the phi function, right? To assign the value here to 1. And then the phi function is going to be like this, right? So you're going to get the condition of the if. And then if it's true, it's going to be x0. If it's false, it's going to be x1. And that's going to be the value of x2 that we're going to assign to double 1. Okay? That's what we call in the compiler literature as the phi function. Right? And then for the conversion, right, into SAT, right, we have here, I will show just some conversion, because as I told you, that's another research. Then we have the simple assignments, right, that we x equal to y. So then you have this conjunction, right, but then we're going to have these equivalents here, x, y, and yi. And I consider here the I as the bit width, right, that I have of my program variable. Then I have the phi functions here. And then how you can translate this to a SAT problem, right? Convert these. Is essentially going to be an ITE operation, right?
Is the effective bit width?
Just the number of bits that we allocate to the variable. Yeah. Yeah.
Like
yeah. Well, in some sense, could be understood, right? Because depending on the context, right, of the assignment of the variable, the number of bits, and then the value that you assign to the variable, you can do some the definition, right, of that number of bits. Yeah, that's approximation, as I mentioned. And then the phi function is the IT operator, right? Which we have the SMT-lib, right? And then the Boolean operations, right? And then one here. And relational operations. So the idea is that we're going to get all these operators that we have in the program language and then translate this to a SAT problem, right? And then from the SAT problem, so then internally, right, they're going to build circuits, right? And then that implement those operations. And well, I don't go here again, but just to show you, then comes is here computer science, right? If you remember your course on digital electronics, right? Computer organization design, blah, blah, blah. So then we have the other multipliers. Then you get the CNF, right? Which we give this to the solver, right? And then also more complicated adders here, right? To model these arithmetic operation when you do the bit blasting, right, of the formula. And so on, okay? Good, yeah.
So this transforms programs into circuits.
Yeah. 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 Because at the end, you're going to have that SAT solver, right? And then you're going to solve the problem, the Boolean satisfiability. You remember your course on design and the analysis of algorithms? The first problem to be shown to be NP complete in computer science. So then you're going to have a digital circuit. And then I'm going to check the satisfiability of that circuit. Yeah. And then all other problems, right, that you have, then we will reduce, right, the Boolean satisfiability here. And there are those circuits here that are. Yeah, yeah. So I don't know who is teaching here at UFAN. It's still Altigrana who is teaching. Yeah. So then, yeah, you are from here, right? From UFAN? Yeah. If you didn't attend that course yet, so you're gonna see later. Yeah. Actually, also in the early 2000s, Haniel can correct me if I'm wrong, but there is such solver, right? And I think that this solver is trying to implement original algorithm. They modify. Yeah. Yeah. Try to check. Look at Z-Shaft such solver. One of the breakthroughs we had was they got those secrets and then try to implement the FPGA, right? And then see how they could boost the performance, right, of Boolean satisfaction. Good. Then just right before I go to the break here, half past 3, we need to stop. Then arrays, shown to you one example here, right, of arrays. Arrays here can be replaced. Hit me here, but we can replace arrays with demugs, right? For example, I have int a with 10 positions. Then I get a at position I assigned to x. And then I can do like this, like the MOOCs, right? So if I is equal to 0, right? So then it's going to be a 0. Otherwise, if I is equal to 1, it's going to be a 1. If I is equal to 2, it's going to be a 2, and so on, right? Our research group, right? So we did some experiments with this. So we have found that, well, seems to be quite effective to replace arrays with the MOOCs, right? When you can determine the value of the statically, right? But up to a certain level, okay? For this case, it was quite empirical here, the experiment that you did. Also with the nested select and store operations, we can also, we have played a bit how you can either create the entire formula and then send that nested formula to the solver, or try to use constant propagation and do the update and select operations, right? That comes here. And then we have here the axioms, right? And the array theory for read and write. So here you can see that, well, in that axiom, if P is equal to R, then when I perform here the read, right? So I'm going to the write. I'm going to write R. Sorry, I'm going to write here V at position P of array A. Even for me, it's quite difficult to read here. And then when I do this, I'm going to do the read of the outcome of that operation, and then I'm going to read the result of that operation at position R, then we're going to get V, because P is equal to R, and then you get V, right? And the same here also for the other axiom that we have. If P is different than R, right? Then we have here also that you do the write of V at position P of A, and then you do read of R, right? And then here is going to be also the similar here if the read of array A at position R. That's quite bad, even for me to read this. Anyway, theory of arrays. We have a bunch of background theories of SMT solvers that you can exploit, right, to model programs. We use the bit factors, theory of array, theory of equality, and these are fundamentals here, right? When you compare here with the SAT and SMT. I always get this question, right? Because people say, well, look, they always compare with SBMC, right? Which was the first bound model checker, right? And then SBMC uses SAT, and then you use SMT. And from our perspective here, right? Look at these two. Doing the SAT solver, so support for high-level operations, as you have seen, you have to convert all those stuff operations to digital circuits, right? There's a positive thing here that while it's easier to reflect the machine level semantics, okay, and it can be extremely efficient because at the end, SMT falls back to SAT, okay? But if the SAT, so you have a bunch of tiers, right? So that Gustav has mentioned today morning. So you have the equality, you have arithmetics, you have arrays. Sometimes you have even quantifiers like CBC5 that Haniel works on. They are quite flexible and extensible, right? In our experience, we say that it requires like extra effort to enforce some precise semantics. An example, again, industrial collaboration. So when we're modeling structs, we use tuples, right? And then the guys from Intel, they love to write structs with bit. Yeah, then we had to extend here the way that you can tuples, right? So the number of bits that they allocate for each element in my struct, right? And then that's what you sell here is enforce precise semantics, right? And sometimes can be slower. From my experience, when I work on this compare SAT and SMT solver from model checking perspective, sometimes the SMT solver could solve faster than the SAT, but in some cases the SAT was faster. But overall, I support verification tools to use SMT solvers, right? And nowadays, after that year 2008, 2009, so lots of verification tools, they use SMT solvers in the back end, right? Yeah, I think I'm going to stop here. There's the part of SMT, right, that I'll probably jump to go to the part that we do the software verification part here with SBMC, okay? Because 1 hour and a half, so good. Let's have a break and then half an hour for a break?
Oh, the break is
half an hour, okay. Yeah, is it ready or should I continue here?
No, it's ready. Let's give some.
Thank you. Yeah.
So we're going to have a break now. Açaí break.
Açaí break.
Kabuki way of talking. Okay, so.
There's a question here. Yeah. Let's.
I was wondering how you, in your original picture, there was a little box about modeling the memory. And I was wondering, in this approach, how do you model the heap in the theory of SMT? Do you use a one giant array per type or something like that? So, and how do you pointer arithmetic and things like that?
Yeah, so we use the tuples, right? And with those two fields of the object and the offset. The object at the pointer can point to, and the offset is going to tell you inside the object which position you are, right? And we also create an array, right, to simulate the heap, right? And then we use some additional fields as well, for example, to determine when the object is alive, when the object is dead, right? With Boolean variables that say it's true or false, right? And but essentially use an array, right, with a mix of tuples, and then with this manipulation of tell us when they are alive or not, and then you do the points to analysis, right? When you do some operation of the pointer, so then there's one bottleneck in our platform is that give that pointer, so you're going to create a nested and sometimes huge ITE, right, operations, because a pointer can point to object 1 or object 2 or object 3 or object 4, right? And then it becomes quite huge, the size of the formula. And then if this guy here with abstract interpretation, that's one goal of his PhD thesis, that we can try to reduce, right, the size of those nested IT operations. To push forward the scalability, right, of the way that you can model pointers.
Pointer aliasing is a big source of static collision.
Yeah, exactly. And even the guys from Synopsys, you know that company, right? Synopsys. We met the engineers of Synopsys. They're quite keen to understand how you model, or how do the points to analysis, and how it could cope with this kind of problem, because they're also facing that in the verification platform that they developed. All right, so, but this guy here, he might have some ideas of how to how to solve, right? Yeah. Good.
Posso perguntar em português mesmo, né?
Pode sim.
Eu tenho uma dúvida. Onde eu trabalhava, nós tínhamos o costume de construir testes unitários e testes de integração. Eu queria saber se estes frameworks que o senhor apresentou, eles são capazes de substituir esses testes unitários e testes de integração, ou é algo para usarmos em conjunto para facilitar esse trabalho? Porque eu vejo que por aí muitos testes unitários que são criados, às vezes são muito acoplados com o código em si. Então, a gente está testando sempre uma implementação específica e se mudar o código, a gente vai ter que mudar o teste. Eu queria também saber se esses frameworks conseguem substituir isso, melhorar a qualidade desses testes.
Excelente pergunta. Ok.
This framework can substitute unit and integration tests.
Eu vou responder em português e tu traduz aí. Ótima pergunta. A gente está agora no processo. A gente teve um projeto em Acceleration Account. Só para dar uma ideia do Reino Unido, ele tem o IPSAC como se fosse o CNPq. E aí, dentro do IPSAC, ele tem um que são projetos IPSAC que eles querem em prática, né, com a indústria. Tem local, SIS, que eles têm exatamente esse problema. E a gente consegue usar isso para gerar automaticamente teste unitário, não teste de integração. Mas teste unitário é possível. A gente passa a prova de conceito com eles e agora a gente está para o próximo estágio. A gente vai receber mais funding para continuar o desenvolvimento dessa ferramenta, melhorando o graphical user interface, melhorando scalability, etc. Para então, é isso aí que tu está falando aí, exatamente está trabalhando também com uma empresa local para virar depois um produto lá.
Muito legal, porque no final os testes unitários, os testes de integração estão muito tempo no desenvolvimento do projeto.
Isso mesmo. Mas teste de integração a gente não colheu não, mas teste unitário é possível, a gente tem uma versão com essa empresa aí que mostrou que é possível gerar esse teste unitário automaticamente, né? E aí facilita muito, né? Quando falou, o cara muda o código, e aí eu já produzo automaticamente nesses casos de teste.
Que ponto a gente tem que manter os testes unitários aceitáveis? Às vezes
Isso.
A gente está fazendo muito mais do que necessário para manter a qualidade da aplicação.
Eu vou falar rapidamente depois sobre essa plataforma lá de geração de teste aí, mais lá para frente, quando a gente voltar. Vou mostrar aí para vocês.
So if I remember correctly, so what Lucas just said was that they're in a step-by-step funding process, which means first step, they did a
proof of concept
for the unit test using this platform, and now after this, they're waiting for the next step to provide integration tests as well.
Yeah, and then create a graphical user interface, blah blah, so that the developers can use it in that scale.
Okay, let's go for the break.
Yeah. Vamos lá. Good. So let's restart here. Can you turn off the light here? Yeah. Good. So let's go now. I just told me that I can stay until 6 here, but where are the other people here? So I think the people from this side, they're still coming, right? There are still 3 parts here. Now I'm going to introduce here further that verification platform for you and show results, right, in terms of comparison with other tools. Then there's the part here of the towards self-healing software with large language models and software verification. That's one of my toys right now. I'm enjoying playing with this code repair framework quite a lot. And then I'll finalize here with the future work in that field of doing hardware and software security, okay? So yeah, an example here of the platform. Now I have various transformations, right, that you perform in the program. So remember, our mathematical formalism here is a transition system, okay? Everything is built around the transition system. And the transition system, again, we have a set of initial states, the set of states, and also the transition that's going to tell me how I can go from one state to another. And the state, we have developed the program counter and developed the local and global variables, okay? For each state, we store that information. And it's the graph, as you can see here on the right. And you add, as mentioned here, the safety properties. We unfold that program up to a given bound. And we do the unfolding. Again, lots of compiler techniques that we discussed, right? That to do constant propagation, do slicing, caching, unreachable code that to remove, right? And then also do the points to analysis here. That was also discussed in the first part. Then you build the SSA that I have already shown to you, okay, before. And we build two the C for the constraints that are assignments that you have in the program, and then the properties that you want to check. And then in the case of our platform, we focus on SMT, okay? Then we use a decidable fragment of the first order theories to model those programs. And we can select, as I mentioned, a specific SMT solver, right, to check that formula. And also use different theories, okay? Here, surprisingly, so we do not only bit vectors, but we can also explore integer and the real arithmetic here, okay? And we can play with both types of encoding with our backend. And then, so we're gonna have a conjunction of two formulas, C and P, where I'm gonna check here the negation of P. So we're gonna look for property violations. So that's the basic overflow that we have. Then, as we discussed, PMC is good at finding bugs, okay? And what about if you want to prove the safety, right, for a program, right? And what here, that was also one of the here. So you have a very basic form of, remember, right, from your undergrad studies, one of the courses that we started learning, that to have the base case, look for inductive hypothesis, and then we're going to check whether the property, right, is going to hold for any value of k of any that I mean consider here proof. For programs, we introduce here the forward condition, right? So we have the base case to find the examples, but then we introduce here the forward condition. If you remember from the first part, what's going to be the forward condition? It's going to be essentially the unwinding assertion that I'm going to check. I want to see whether it holds in all states reachable k unwindings. The unwinding assertion that I have seen before. Okay? And then it comes the, and this one, again, we inherit from F. So what to do here, we get the loops, and then we identify the variables in the loops, right? And then you havoc those variables. What does it mean? It means that we introduce no determinism, right? To assign no deterministic values to the variables that participate in the loop, okay? So then what are going to do here? You are going to, okay? And then when you override the loop, so then you consider the loop invariants, right? Again, for design and analysis of algorithms. I'm just when I teach that course, because the textbook that we use, the common textbook, Yeah, they mentioned about correctness of algorithms, but it's quite shallow, right? I start introducing the notion of total correctness, partial correctness, loop invariance, recursion invariance, and they say, oh, look, guys, it's not in the book. So yeah, it's not in the book, but you have to learn that, right? If you want to design algorithms that are correct, okay? And then, yeah, then you compute that loop invariant. So you add those loop invariants here in order to constrain, right, the search space because we have over-approximated the loop. And then we assume the loop termination, and we check whether the property P is going to hold for any K, right? And you do this in an interactive manner. So then we start with K1, check the base case for the condition step, and here's the algorithm that's going to, right? So as you can see, in the base case, right? So if you find a property violation, we return the trace. And see, that's an interactive algorithm here, okay? Then we go to the fourth condition that's going to check the unwinding assertion. If the unwinding assertion holds, we return true. Because check, we have checked, there's no count example. Now the unwind assertion holds, done. The program is safe. If not, we go to the interactive step. Then you do all those transformations that I told you. And then if it holds, then we return true. Otherwise, I will just keep in this loop here, okay? So here you can see the transformations that to apply for the program. So the blue one, here you can see that, well, what we call is unwinding assumption. Okay, that's gonna be the condition that I have of the loop that you can see x greater than 0, and then that unwinding assumption is gonna be essentially the negation that we have here. It's going to be x is smaller or equal than 0, right? And then for the base case, what I'm interested here is just to find bugs up to the depth k, okay? If I don't find the bugs, so then I go to the next step. That's the fourth condition, and check. Oh, look. Now let's check the unwinding assertion. That's essentially the negation here, okay? X is smaller or equal than 0. And well, if it does not hold, then you go to the inductive step. And then as you can see here, right, that we put the loop termination. Also, we ensure that the loops execute at least once, right, if that's assumed. And then if the assertion holds, okay, so then you can tell that it can hold for any value of k here. So the basic framework that we have for proof of induction is simple, right? So the colleague here was mentioned about IC3. That's quite far from what IC3 does, right? And the property directed reachability PDR algorithms. Well, it's quite efficient. It helps us to find some proofs of some programs, right? And then what helps the k-induction is that part of invariant generation. So we infer, as you mentioned, the invariance based on intervals, right? That we build as abstract domain by the dependency graph. And then you can support here, compute here the minimum and the maximum, right? Right now we can handle integers. Floating point is something on the way. We have some partial support. So we essentially disable because it's a bit, it's still unsound, our implementation. But for integer, it's very stable, right? And then we inject these intervals over integer variables with assumptions, right? Contract then VSSP that I'm going to show you an example. With that goal to remove the unreachable states, right? So here you have a very simple example that you cannot see well, right? How we can compute, right, those intervals here for each line of the program. I'm going to show another example in another slide. But in general here, when you compute those intervals and then tell the minimum and maximum value of the variables and then put these intervals as part of the proof, right, of the k-induction, it helps, right? So they have a Taka's paper in 2019 that to show that our results, we get like 10% more verification tasks verified when you do the k-induction with invariants, okay? That's the paper here that you can check. And then, so that now goes to the work of Raphael, that's here, right? How you compute intervals in SBMC. Just a few slides quickly. So I'll have the notion of the intervals, the lower and upper, right? Of the lower bound and the upper bound. And the lower has the property here that's always less or equal than upper, right? And then here we'll have an example that have that variable a, right? If a is smaller than 50, so a is going to be 3, else a is going to be 5. And then you compute the restrictions for intersection, right? Here's an example of the intersection, right, that have minus infinite plus infinite, and then with the intersection of minus infinite and then 50. And when you do the intersection, so you're going to get here for that if minus 50 to minus infinite to 50, and then here from 50 to infinite. And merging here, that I'm going to compute the value of a, right? It's done by the Hall operation, where I'm going to compute here what would be the interval for the variable a here. That's going to be 3 to 5, right? And the most important is that we add these, as you can see, as assumptions in the code, okay? So we have here, again, we could give here just one talk about abstract interpretation, right? So that's not going to be my goal here. And overall, abstract interpretation, I can tell you that helps substantially model checking. Again, so in one of my conversations with Daniel, so in the past, Patrick Cosso and Edmund Clark, they got together, right? Patrick's from abstract interpretation, Edmund from model checking, right? To see how those two fields, right, could combine, could be connected. And well, it is quite promising. We are now making progress, not only to support here, as you can see here, integer, but also extend this to floats and then do the points to analysis, right? Use abstract interpretation to improve the points to analysis so that you can reduce the size of the formula that you give to the solver. Okay, good. And then once you get those intervals, you apply contractors. And then you cannot see, right? So it's good that you try to replace this data show tomorrow. So I cannot even read myself here the example. But anyway, so you get the program and then you compute here the domains that you cannot see clearly the value of the variables. But there's a figure here, right? So here's the interval that you compute via abstract interpretation. And then when you apply contractors, in particular here, the backward contractor, so it's going to remove that area in red. And then it's going to remain just the area in orange to be checked, right? Because, well, I'm just interested here for this particular program, right, to check for this constraint here. And when you do this computation here of that area, so we add the orange area here as another assumption here, right, that you can now prune here the state space exposure that will be done by the solver. And that gives very positive results here when you apply contractors. Overall, right, in our assessment, in our evaluation, consider here the benchmarks that we have in the software verification competition, right? So overall, the performance of this technique was not that great, right? But for some particular categories, especially when you check for reachability safety, right? That helps quite a lot to prune the state space exploration here, okay? That's already implemented as default in our platform, but you can also give options here for the user, right, to enable, disable that part of contractors, use constraint programming. And how it looks like, so very soon we are going to see the results from 2024, right? But these results here from 2023, that was the competition that started last year, right? So it's usually around October that we start the competition. So we have, in 2023, we had like 23,000 benchmarks. Those benchmarks, they include the Linux device drivers, Windows device drivers. They have also code that Amazon, they contribute to have some open source applications, right, as part of some categories. And we have many tools, more than 30 tools that participate in the competition. And we have different categories, right? We have a category for memory safety, category for reachability safety, category for concurrency. And there's also the overall that's going to combine all those categories, right? So then the graph that I show here is for the overall. And here in the X are the scores. And the scores computed as follows. If the program is safe, and then you say that's safe and provide invariants, and then those invariants are double checked by another tool, by a witness checker, you get 2 scores. If the program is unsafe, and then you say that's unsafe and they provide the counterexample, and then the witness checker is going to validate your counterexample, then you get 1 score, right? So because we also know that to prove the safety, right, is harder than refute the property, okay? That's the way that you get the scores. And here's the time. Here the time is actually in seconds. If you take a look, right, here, 10 seconds, right? So that you cannot see, but you can trust me. So in 10 seconds here, so you are the tool that can solve most verification tasks in the international competition, right? If you give extra time, right, like here's more than 100 seconds and so on, there are like 3 or 4 tools here that I can see very well that perform better than us. But all these tools here, they use a portfolio-based approach. What does it mean? It means that they use more than one technique. They get one technique, they give like a time, 300 seconds. If it does not solve, now try another technique, more 300 seconds, and so on. In our case, and also the Automizer, which is an automata-based verification tool, is just a single technique that we use, right? In this case, we go with the decay induction that you have seen here, okay? And then, Lucas, if you compare to other PMC tools, right, that you have in the competition, so here's CBMC, you can see that the shape of the curve is very similar, right? CBMC and the SBMC here. And the main difference is that we can find more programs that are safe and also refute more properties in programs. That's what gives this difference here. There's also another tool that you cannot see here, right? That's QLS that also does symbolic execution, okay? And then also there's the shape you cannot see as well here, but the shape is quite similar as well, right? Again, you can solve more verification tasks than QLS. And so then the other tools, we have one that's based on CLI, right? So some of you might know CLI, which does symbolic execution. Is symbiotic, and then I can see here in this graph because it's not, I can see from here. So symbiotic is here, is this one here, symbiotic. You can trust me again, right? Our expectation for this year is that we are gonna push this forward here. Stay tuned, right? Go to the SVComp website. Very soon they're gonna announce the results. This year expect to get closer to Automizer and also this other portfolio-based approach. So push forward here with this curve. Right. Good. Questions?
Does Galois Crucible participate to this?
Say again?
The company Galois.
Galois?
They have a symbolic execution. I think it's Crucible.
Let me see here. The HLS, Bubax, MMC, CDT, CPA, Divine, SPMC, Coblint, Graves, Pesco, Kojak, Tapan, no, it's not here. Yeah. And Infer, the organizer has invited the guys from Infer to participate in the competition. Right, I think Haniel has experience with this as well, but while they didn't, they said no, right? And then what the organizers did was, okay, then download the tool and integrate in this framework here. And it was terrible. It was terrible, the result, the outcome. Gustavo, you can check later in the website competition. It gives lots of incorrect results. But again, the developers could come and say, look, yeah, there's some problem here that they can fix the tool, right? But they didn't want. And it's good that we compare, right? Because as Gustavo pointed out, Infer is used Meta. And how Infer compares to the state of the art here? We have CMMC, the guys are brave, right? Because CMMC is used at Amazon, but even so they participate, right?
My understanding of Infer is that they're very much focused on
separation logic.
Yep.
And my understanding of IFER is that they're very much focused on separation logic in order to handle aliasing problems with pointers and memory.
Yeah, but they don't have the memory safety category that they could, in principle, participate, right? I attended a talk from G. Stefano at TACAS, right? TAPS. Yeah, they say that they use even for concurrent programs. They use for everything that Facebook, so they could be even participate in all categories, right? I don't know. Daniel has expertise in SV Comp, right? I have some that are by companies and they don't submit, right?
Yeah, the main thing is so.
So in the SMT competition, which organized for a few years, we had a similar situation with Z3, where they don't care to submit it themselves, and then we will always contact them, we will include that they will not submit, so we just did it. And in a few cases, we had a similar situation that there were a few issues that they could solve, but they chose not to.
I see, yeah. That was the case for Infer. And then the organizing put in this overall category, right? But you can see the data on the website.
And the follow-up, I think Chris participated with Crooks.
What's the name of the tool?
Crooks.
Crooks.
CRUX.
There's another tool that's quite famous, Framacy. Also Framacy, Rafael, if you can remind, didn't perform well as well. They were invited to participate, but they didn't want. They organized theirs integrated, and the results were not great as well. Right? Yeah. Good for the questions here.
Just talking about Framacy, some of the tools like Framacy, the specification language. So they work with sort of assumed guarantee contracts, and the specification language can refer to an externally defined logic, like the logic of maths, let's say, with which they express functional correctness of the code with respect to maths. In the assertions and the assumptions that you can write in the C code, are you limited to just writing conditions as effectively C programs, or can you also refer to some kind of external logic with which you can prove the functional correctness of the C?
For example, using some quantifiers, or
I don't know. For instance, if you want to show that a binary tree structure correctly implements a map or a set, or with addition or operations, you would probably, if you were to prove functional correctness, you would like to say that, well, this piece of C code actually faithfully implements something which you define in kind of math, and it's not really a memory safety issue.
Yeah, so I need to write what I jumped here. Yeah, that's the what you have here that you provide, right, for the developers. The assert, assuming they know that, right? And then you write something like this, in that style, that have the assumes, right, the asserts, the no determinism here. And then to check for some particular operation, right? So you need to write some extra code with those primitives, right? So that they can.
Right. So I guess the question is, what's the language of what you write in those assumes and asserts?
Yeah, just follow the C. Just follow the C. Yeah, just follow the C. Yeah. Good for the questions? No? Yeah, let's move forward here. Yeah, so yeah, that was here. Good. Now a bit of concurrency. Right, because if you remember well, the model checking always, so they one of the motivations, right, was to verify concurrent programs, right? And when you talk about concurrency, as I have shown to you here, right? So we have not only the data, the non-determinism of data, but also the interleavings. And it becomes, when you find a bug in a concurrent program, right, from the perspective, it's quite hard to reproduce. Because as you can see in that draw that I did here, imagine that the bug just manifests because of one specific interleaving, right? Then sometimes what happens with the developer is that, the tester has found the bug, reports to the developer, but the developer is never able to reproduce the bug. And it happens quite a lot, right? Developing tools, right? Automated reasoning tools that you can give some assurance, right, about concurrent programs, that improves quite a lot productive, right, of developers. And we can look here, there are two kinds of errors, right, in concurrency that you call here as progress errors that are related, for example, to deadlock, starvation, which are typically caused here by the wrong synchronization that you have of mutex with lock and unlock. And also the safety errors, right? So if you take a look at the literature and then see the common concurrency bugs in open source applications, the majority of those bugs, right, they are related here to data race. And data race is the situation that, I have two threads, and then they access the same location in the memory, and then at least one of them, they perform a write, and the other one a read. And then I have a data race, right? So if both perform write, it's also a data race. But if both just perform the read, so there's no data race here, okay? It's quite tricky, right, to find data race in concurrent programs, because sometimes, right, that data race happens because of a specific interleaving. I can tell that the support that we have for data race, one of our main challenge here is when you have pointers, right? And then you get the following situation: you have the threads, and then those threads, they manipulate the pointer can point to different objects in the memory, and then you manipulate the data, right, in the memory with read and write. And then to know in a given program location, right, when you have a data race happening because of those point operations, is not an easy task. It's not easy, right? So that's something that we're developing also in our group. So we have support for data race for no pointers, but it is a bit limited yet, right? The support that you have. And Lucas, what about the state of the art? I can tell just based on the competition, right? Also, I don't see great performance of the verifiers to find. It's quite surprising, right? To find the data races in concurrency programs. There's still some research that can be done here. The guys from CSEC, that they do sequentialization, right? That they get the concurrent program and then they produce a sequentialized no deterministic program. They have done some research, right, on data race checking, but it's quite limited as well, what they do. Good, and then you have two program styles here, okay, when talk about concurrency. One that's message passing, right, which is truly parallel distributed systems, where you have the different machines, right, that they can exchange message between them. And then the shared memory, which is more our focus here, right, that's more in the domain of embedded systems, where they share, right? I have different cores, and then I have the memory that are going to share a given position, and then they can communicate via that shared memory to exchange information, right? So one, we use the message passing, the other one, I use the shared memory so that the threads can communicate. And the research that we have done so far, right, in that field, focus here on, okay? And then if you talk about C programs, typical implementations, right, of C, they use the POSIX pthread, okay? And I have seen a lot of re-implementation of software systems that use pthread here. Especially, I don't know if you remember, when I worked at NXP Semiconductors, so they had the set-top box with 2 cores. And they just modeled with pthreads, right, to do communication with the threads between those cores. We can here create and destroy, right, those threads on the fly. We can also bound the number of the threads that you can create here for the verification part, right? We support here, consider here this implementation of P-threads, can have multi-threaded programs with loops, recursive function calls, and so on, okay? And then you assume, as I mentioned before, the sequential consistency, right? So you have to perform the read before the write, and also you can just, in this case, for example, execute here. For example, in this case, B1 after have executed A1. We don't do memory model, but also weak memory models is also another big field of research in concurrency, right? Where I have no assurance of the sequence that those instructions can be executed. What people usually do, they convert weak memory models, right, to sequential consistency using some off-the-shelf verifiers, right? Here in the state of the art, in this era of BMC frameworks, so in our case here, we have two algorithms. One that we call is lazy exploration, that we individually check each interleaving that you have in the program by build a reachability tree, okay? And then we explore a given path in that reachability tree, and then when you don't find a property violation, so you backtrack to the unexplored node, and then keep the exploration, and then we can have an exponential number of interleavings. So then you do the context bound, right? So that was a technique that was proposed in 2000. It was a Taka's paper 2005 by Chas Kadia at Microsoft. And then they have shown that, well, in the Microsoft applications, to expose the majority of the bugs, you just need 2 context switches, right, to expose most of the bugs. And means that, well, we can context switch from thread 1 to 2 and then back, and then I can expose most concurrence bugs. Then you do this, right? I implement this context bound, use this lazy exploration, and then also have the scheduling recording that you can build one single formula with all possible interleavings. But as I pointed out before, one of the main problems here is that you can explode, you can blow up the SMT solver, right, with the size of the formula. Then SBMC also does the encoding of all possible interleavings in one single formula using partial order method. It was a CAF paper 2013 that they published. And then it comes the sequentialization method, right? That you get the concurrent program and then you convert to a no-deterministic sequential program, right? And it started with the keys, right, of Chas Kadia. Then we have the law reps, right, the eager sequentialization. Then the colleagues, the group that I was working in Southampton as part of my PhD, they developed the lazy sec, the memory unwinding. So there's a lot of research in that field, but there's still things to be done. I don't think that the tools that are available here, they can solve verification problem comes from the industrial setting, okay? And then I can tell you this because our collaboration with Army. Army wants to formally verify low-level code that has the multi-threaded characteristic here. And they don't have tools that they can handle the code that they produce, right? Yeah, and then here, just go quickly what to do in terms of concurrency. So then we do a combination of symbolic model checking that I have presented here to you before, right? Where you symbolically encode all the states, right? Also do a explicit state model checking. What we're gonna do here, we're gonna explore all possible interleavings explicitly, while each interleaving is encoded symbolically. All right, so that's a combination of those two techniques. Then you also do, as you discussed here before, the state hashing and also a bit of partial order reduction to reduce the number of interleaves that you have. That was a paper at ICSI, which got, as I told, the distinguished paper in that time. Here's an example, right? So that you build a reachability tree. And then you have information about the active thread, the context bound, global and local variables, right, to indicate my initial state. And so then we get the program, and then we have a set of rules, right? When you get a fragment, right, conditional, no conditional go to, assume, assert, perform a operation for those instructions, right? So then you're going to expand this reachability tree, right, based on a set of rules, okay? And then when you get to the leaf of the tree, right, so then we code this path symbolically, and then call, right, the SMT solver to check the satisfiability, right, of that path. It's something like, as some of you might know, CLI, right? That CLI does also a symbolic execution by exploring each path in the sequential program, right, individually. And the problem, again, also with CLI is that we can have an exponential number of paths, right? Yeah. And then there's no bug, then you backtrack, and then explore the next unexpanded node, and then continue this exploration, right? And then we start, and you have right, check all possible interleaves for the right. So that bound exploration, okay? Yeah, and then do this when you build the tree. You also can use symbol execution, right, to determine check whether a given path is blocked or not with the mutex operations, right? And yeah, then we have here the full expansion of that tree. Here, just to give an idea, consider here this the thread to stage and the thread reader. Okay. Also, so we have val1 and val2, which should be updated synchronously, right? Those are the verbs that here, val1 and val2. And here I have my program state. That I have the program counter that's going to tell me where I am in the exploration. Then I have my mutex, right, with M1, M2 in the program. The global variables, val1 and val2, and the local variables T1, T2, that's here in the second thread. And so what happens? So again, M1 to val1, then we unlock M1, you can follow here, right? And then we context switch to thread reader, and then I'm going to lock M1, and then I'm going to check if val1 is equal to 0, right? Which is this case is not, because val1 is 1. Then T1 is going to be val1, then T1 is going to be 1, and then I unlock M1, go back to thread to stage, lock M2, then assign val2 is going to be val1 plus 1, right? In this case it's going to be 2, go back to the thread reader, okay? Lock, and then this is going to hold, right? That's one interleaving, right? And yeah, the was it's unsatisfied, means that the assertion holds, okay? And leaving, so I'm gonna faster now. So then I execute these three statements in thread to stage, then context switch to read, right? Then I execute fully the thread reader, go back to thread to stage, right? And then when I finish here the thread to stage, now the value of T2 is going to be different than T1 plus 1. And then the assertion here fails, right? And then produce the counter example. Okay? That's the way that we typically explore the interleaving, right, in a multi-threaded program. The state of the art. There's this paper that was published last year in a very important venue in our field. That's the ACM transactions, that's topless. The ACM transaction program language and systems, right? And you cannot see the numbers here, that's terrible. But the authors of that paper, right? So they have done an extensive evaluation of various model checkers in the field, right? And then here, essentially, for example, they compare different versions of CBMC here, and then you can see the number of cases that CBMC can solve, right? Also, the number of cases that they miss property violation in the program, crashes in the tool, timeout, right? And so then here with SBMC, SMAC, and Yoga, right? So in terms of the number of programs that you can prove safe or unsafe, that is 800. So that's very close here also to SBMC, right? Which is 700 something. You also have some crashes, some timeout, and then we miss 3 bugs here in those concurrence programs. While the others here, you see SMAC 279, right? Yoga, CBMC 35, CPA Checker 643, right? And so on. And then you can see that, well, the approach seems to be a bit naive, right? But it performs relatively okay, right? If you compare with the state of the art, right? Good questions here about the concurrency. I'm gonna go to the part of the multi-threaded here. Oh, to this test generation. No? Good. Let's go then. When you started work on that part of test case generation, we took that platform that we developed, and then now let's, in a naive way, to produce test case. What's the naive way? We already do the transformation for the intermediate representation that you learned here today. We add the checks for errors and code coverage that you have seen here before. Not much difference. Then symbolic execute intermediate representation, produce SSA, you have seen. Translate this to a logical formula from SSA, you have seen before, okay? But the difference now, quite simple. What we're gonna do, we're gonna solve the formula interactively to cover errors and goals. Why do you do this interactively? Because you want to get the inputs, right, conditions that comes from the count example to produce test case. Okay? Luca, does this approach perform well? Was average if you compare with other techniques. You have to go further, you have to do better, right? But when you start with something simple, and then we start improving it, right? And then what you did was to build this engine here that we call it comparative verification, right? That we have different engines here. We have the BMC. We have a selective conchoic fuzzer that we develop in-house. And then we have AFL, which is a gray box fuzzer, okay? Developed by Google. And we have here Tracer, right? That are gonna get the program, do all the manipulation in the program, introduce goals to the program, and then use this Tracer in order to establish a communication between different engines that you have to produce test cases, okay? And also exchange information between these engines, right? So that you can explore further and further the state space exploration of the program, okay? And in some sort here, so you have what calls comparative, because they communicate in order to solve a goal, right? That's to produce test case that can improve code coverage and also find bugs. And then, well, this approach here, we go further, complicated it even more here. We start also compute here. You have seen in the conchoic, in the selective fuzzer here, we used to get the variables, right? And then compute the intervals, and then choose random values in that interval. And integrated here from a C as part of our solution, right? That you can use from a C here in order to compute beta intervals, right? That's quite bad, right? The diagram. we really need another data shown here. And then these with from a C, so together with contractors that I have presented to you, so it could come up with beta intervals to improve the selective fuzzer that you cannot see here in this figure, okay? And they perform with the state of the art. The tool that develops called FuseBMC, that's the red one, right? So here is the overall category that combines produce test case to improve code coverage, or the category produce test case to find bugs, and another category combine all these cover branch and cover error, right? And so then here, right? So then you get the scores. When you find a bug, you improve the coverage, and here's the time, okay? So we have Fuse BMC, that's the red one, and also Fuse BMC with the contractors in pharmacy, that's the gray one that you cannot see here. And the yellow is developed by a company, right? That's called, the name of the tool is Very Fuzz. And for 2 consecutive years, Fuse BMC has always been on the top here of this competition, which is part of ETAPS, right? That's the European, that holds the TACA's phase, and so on. Yeah, also for reference here, we have CLI, right? Which is also quite used for software testing. So CLI, here's this one, brown, that you can see here. And then you can see the different performance here of that solution with CLI, right? And that's the framework that we're using to work in collaboration with that industrial partner that I mentioned to you before. Aquela questão, tua pergunta sobre a geração de teste, em cima dessa máquina aqui de teste, de gerar teste. Né? Good. I can see that you guys are quite tired. I'm going to do the following. I'm going to jump here for the code repair part, because as I told you, is one of the toys that I have now in Manchester that I'm quite interested in solving that problem. Unless you want me to go on here with... Edja. I can see that you guys are tired. Let me jump here. Yeah, these are now applying this framework to verify open source applications. Here's the Wolfram QTT that was done by one of our PhD students. That was the original design of Wolfram QTT, and then after you detect a data race bug in Wolfram QTT, so the developers, they change the architecture, right, based on the bug that have report. So here, you can see all the discussion in GitHub, right, that our PhD student had with the developers. And she also got some presents from the company because of it was a quite important bug that was solved in their platform, right? And yeah, the group was quite happy for her achievement to find this bug. Good, so let me go to this part here of the code repair. As you have seen, so the large language models are quite successful, right? And in that area of code repair, so the idea is that you have the original code, and then you try to propose a patch, right, for that bug code. And then you can have 3 outcomes here. Either you produce a patch that's going to fix the code, or there's no effect in the patch that you have produced, or introduce new errors. And as I told you, it's not only deep learning models that you can achieve that, also with developers, right? So also developers, sometimes they fix a bug and they create another, okay? And then what we want to do here, right, is, okay, so let's look in these deep learning models. In particular, let's look at the success of large language models, right? And then see how you can use large language models here, introducing verification in the loop. And then the idea is that, well, we have the original code, okay? Then we have our BMC engine. That's going to tell, look, if there is a bug in a program, I'm going to give the code plus the counterexample to the large language model, okay? And then the large language model is going to provide here a patch to that bug, okay? And then we're gonna now use the model check to check whether that patch solves, right, the bug. Where you are, there are still open research questions here, right? So when you produce a patch, it's difficult to give you assurance that the patch does not introduce new errors. We can check for specific property, like as I'm going to show here. For example, buffer overflow. There's a buffer overflow. Now let's fix this buffer overflow, okay? And then you manage to do that. But you can change the original semantics of the program, right? And then you can tell Lucas, then apply equivalence checking. Give the same input, they produce the same output. But it's not going to work, right? Because the program was buggy. We fixed it. They are not the same program anymore. Full equivalence checking is not possible. You can do partial equivalence checking. And that's the research question now that we're trying to solve, right? To see how we can do partial equivalence of those two programs so that we can ensure that we don't introduce new bugs. We don't have that answer now, right? But what I'm going to show to you is for one specific property, how the technique performs.
Another aspect is in that kind of verification, properties that you check are also part of code in the form of assertions and assumptions. Nothing prevents the LLM from, let's say, assume false.
Yeah.
So how do you prevent from?
Yeah, you need to work out on the prompty language, right, that you use to communicate with the LLM. In order to avoid that kind that they can introduce some unexpected instruction, right? Yeah, that's the prompt language. I'm gonna show here. Okay, that's the basic idea here. And then we use here ChatGPT, right? So you guys don't laugh, right? Formal methods here. ChatGPT, formal methods, right? And the BMC engine. Well, I want to make sure that it does not cheat, right? Yeah, I want to increase here the trustworthiness, right? What I'm going to tell you is our journey, okay? And remember, for you guys, everything in life is a journey, right? So you go from here, and then you end here. For you that are doing MSc and PhD, we are going to tell you a journey later, right, for the examiners, right? And what I'm going to tell is our journey here, how to do that self-healing software. We got here the ChatGPT, right? And then, so you cannot see. You really need to change this data show. It's going to be terrible for tomorrow, right? Nobody can see this. But there is a lot of arithmetic operations here, okay? And we asked it, when I wrote these slides, we asked ChatGPT if there's any problem with this code. And ChatGPT said, look, there's no problem. Okay? And let's give this to BMC Engine. Give to BMC Engine and say, well, there's an arithmetic overflow, inline blah, in that operation, and then give the count example. Right? And so then you give this to the ChatGPT, right, the code and that count example, and then, provide a solution here, right? So in this case that you cannot see here, it has replaced the type of the verb instead of being integer by being long int. It solved it. Say, well, good, right? And I can tell this experiment, this initial step was in one of my lectures in software security. What I like to do is like to give research problems for the students to prepare seminars. And then the guy came with this approach here in that course. And then let's do an experiment with this now. Okay, so here's the setup for the code generation, code repair. Okay. We have generated, using ChatGPT, 1,000 programs with the following prompt that you cannot read, right? But you can get my slides later. And I'll say here, generate, in this case, it was a quite small experiment, right? Just for us to understand what was happening. Generate a minimum of 10 and maximum of 50 lines of C code. Use at least 2 functions. Use strings, arrays, bit manipulations, and string manipulations inside the code. Be creative. Always include every necessary header. Only give me the code without any explanation. No comment in the code. Yeah, that's a good. I'm going to show later another experiment that I have done, okay? And then one of our main concerns when we started, we did this work in March of this year, okay? There's an archive paper about this. We were concerned about code generation. So are these ChatGPT models able to generate code? Nowadays, you can see many papers, right? So now I know that LLMs are quite good at producing code, okay? But then the first research question was, what the state-of-the-art GPT models capable of producing compilable, semantically correct programs? And the second one, okay, if you answer that research question well, can we give external feedback to LLMs so that they can improve the ability to produce patches to programs, okay? Surprisingly, here, as you can see, for small programs, for two properties, buffer overflow and pointed reference, we could here produce 99.9% of compilable programs, okay? And also, in this loop here, fix, right, 8% of the benchmarks between 1 and 3 interactions here, you use LLM and formal verification. Then we got very motivated in this domain. What we did next? Now let's make the problem harder. Let's produce now more than 100,000 benchmarks, right? Independent and compilable C programs. Now, a bit longer, right? Will vary between 50 and 600 lines of code. By the way, this paper I'm gonna present on Friday at FSE, Formais. That's a conference co-located with FSE, which is also a A-star conference software engineering. Then you use here the ChatGPT, right? Produce, and then you get the GCC, then get the warning message to improve the code generation. Then produce these programs here, right? That we store in a data set. And then you use SBMC to label the programs, okay? Then comes the part here that you asked me, right? About the prompt language. So you want to show diversity, okay? Then you create a prompt language, right? That you have here this format that I can read for you, but then with different style and different type. Okay, I'm gonna read here. So write a unique C, then the type, sort in example program in a style, multi-threaded program style. Structure, minimum 50 lines, be creative, do not say I'm sorry, always come up with some code, make sure the program compiles, runs without any errors, please generate a code snippet that starts with C and ends with the dot. I can see here with the apostrophe. And then the type, here you have graph representation, memory management, file handling, encryption, table game, and so on. It's quite huge. And the style also, multi-threaded, happy, realistic, scientific, creative, authentic, and so on. Okay? And look at how does it compare with the state of the art? You cannot see here, unfortunately, right? But here's our Form AI data set. It's the first AI data set in the literature that was we use LLM to produce code as part of this data set. Was the first one. More than half of these benchmarks, they contain vulnerabilities, okay? We have programs that are part of this data set. Some of them, they just producing functions, right? But in our case, I have programs. And then you also label the vulnerability according to the common weaknesses enumeration. Here's the average number of lines of code and the methods that you have used to label, right? The data set. That's how it compares with the state of the art and how it looks like in practice. So then here is a table about the frequency of the keywords that you can find in the program. And here is a table that shows you the number of unique vulnerabilities according to the CWE, the Common Weakness Enumeration. In this case, we can check for 42 unique security issues in the code that has a direct mapping for the CWE, which is quite vast, okay? Lucas, how these CWE are relevant in the industrial domain? Well, if you take a look at the CWE, the top 13, right? So then we can tackle here 6 of them with this data set. Out of bounds write, the first one, right? Improper input validation, out of bounds read, use of the free, no pointed reference, integer overflow or wraparound. Okay, so then you can see from the industrial perspective here, right? So this CWE collects vulnerabilities in real applications, in open source applications, right? So then you can tackle nearly half of those top 13. No. That was our work. We did this.
Because I already tried to solve concurrency problems using ChatGPT. It was horrible. Didn't solve any of these problems. Have you ever thought about like send this to the OpenAI to they implement this on ChatGPT?
What do you mean by sending?
To put in ChatGPT available for the people to use and solve problems using ChatGPT, problems like concurrency and other problems like that.
No, never. No, we didn't have any communication with them about this. Yeah.
Would be useful.
Yeah. That's gonna be useful. Good questions here. Yeah. Good. So then going further here, you guys cannot see anything here. So let me just check here. So as you have seen, the data set is huge. More than 100,000 benchmarks. A lot of diversity. Okay. And then comes the question. So what are the best parameters that you can use to find vulnerabilities in this data set? Use our verification engine, right? And then you have to consider here, let's use plain BMC and K-induction. Plain BMC just look for bugs. K-induction also want to prove the safety. Okay? And also let's play with the number of unwindings of the loop that I have explained here, right? Let's unwind 1 time, 2 times, 3 times. And then have create a table here with different parameters, right? And also collecting the timing and the number of vulnerabilities, right, that you can find, and also the number of programs that you can say that are safe, that you can see here. Verification successful, verification failed, timeout, and some error. And then use plain BMC, unwinding of 1 and 30 seconds for verification tasks. So that was the best result that you got here, because you could verify the entire data set in 30 minutes, okay? So then our parameter here that you cannot see, right? So then we are gonna now run this data set to label the data set, check if overflow, memory leak, pointer saved, array out of bounds, right? Then do multi-property verification. That's crucial, right? Multi-property verification is a very important feature in verification engines, because, well, you get the program, you can have more than 1 property in the program. And then you need to be able to check all those properties at once. That's what we call as multi-property verification, right? And then especially for bug hunting, so that you can have many properties, then the program can have more than 1 bug. I want the tool to tell me what are all possible bugs that I have in the program, right? And then you have that support in our verification unit that's called multi-property. And yeah, and then you unwind the loops just once. So that was the command line that I have used here. And good, so that was to label, and now comes the code repair performance, right? If you remember, we started with a very small data set with 1,000 benchmarks. With just 2 properties. Now it's 112,000 with many properties. Now it's a hard problem to solve, right? And then you can see that the accuracy has dropped from 80 to 35, right? And here you can see in this case here, from that 1,000 program samples that we have randomly selected here from this 112,000, that's more or less 355. So in most cases, we have sent the code and the program violation to LLM, and then has produced a patch, and that patch fixes the vulnerability according to the limitation that we discussed here. And then here, around 8 cases, there was 1 try, right? Then around 60 cases with 2 tries, and then you can see that start decreasing, right? It means that, well, as you go further here, so the chance for the LLM to repair the program is quite difficult. And then in this graph here that you also cannot see, we have here the type of properties that LLM is good at fixing in the code. And well, in this bar here, you can see that LLM was very good to fix array bounds violated. After that, the reference failure. After that, arithmetic overflow on shift operations. Then buffer overflow on scanf, and so on, right? So that's all the types of bugs. And then you can see how the LLM can succeed in some of these vulnerabilities to be fixed. Okay? Good questions here? Daniel, I see that you are tired. A lot of information, right? So everything is available online, okay? That's the Form AI data set. Be careful with the data set, right? So you put here. If you try to compile and run, it can destroy your computer. Yeah, I'm not joking, right? So it's gonna connect to the web, scan your local network, delete a random file from your system, right? So it can do many things, bad things in your computer. Well, you want to produce a diverse data set, right? Okay. Good. So then the final part here. I'm gonna go quickly here in the final part. As I told you, so in the UK, the government, so they say that everything is digital, right? And there's a lot of funding in the UK government to do research in computer security. And there was a program that was called Digital Security by Design, right? That they nearly 200 million British pounds, right, to do research in security. And most of this money, right, they invest quite a lot in this platform that was developed between Cambridge University and Army, that they call it Capability Hardware Enhanced Risk Instructions. That, as I told you, so they introduced some additional instructions to the risk architecture, right, in order to give it to for pointers, right, what they call as capability pointers, to indicate when a given point is going to point on outside the boundaries of the object, and then detect this in the hardware level. Okay, just to give an idea here how it works. Do here as a hybrid approach that we can include the cherry.age, and then indicates here the pointers that are capability pointers, right? And those capability pointers you cannot see here, but then they add extra information, right, about the possible objects that the pointer can point to. You cannot see here well, right? But it's going to consume more bits, right, more memory, also a bit more overhead. And then indicate this in the program, the pointers that are capability, and they also set here, define the bounds, right, that pointer can point to, okay? And then they'll carry this information here. You can do this via the API, or you can use Clang. There is an extension of Clang Cherry, okay, that they can do it automatically for you, for all pointers that you have in your program, okay? And then here, well, related to SBMC. Remember, our design decision was to use compilers here via integrated compiler via the AST. So then we got here for free. the work done by Army and the University of Cambridge, right? So they have cherry clang that's going to indicate the pointers that are capability pointers. And then apart from that, then you had some work here that you had to model, right? To create operational models for the cherry C API. Operational models for us, so you determine here pre-post conditions and also some code that simulates the behavior of the library. And they also extend here our memory model for cherry, right? To introduce here the new capability types, right? The capability pointers, because as you have seen now, the pointers, they have a different size because they care additional information, right? Of the object that the pointer can point to. And then you had essentially to develop these operational models here for the API and also extend our memory model. And what I've seen, right, for the vision here for the group is a platform like this, right, that we have here. AI code, source code, and binary code. Lucas, do you do research in binary code? Not yet. I have submitted a proposal, didn't get accepted, unfortunately, but yeah, it's our pipeline to also do binary code, but we do source code and then start doing AI code here. And then we have our automated reasoning system that's gonna explore searching, learning, memory, and parallelization to do this task here, that you can detect vulnerabilities, can classify the vulnerabilities, as you have seen here, right, that work with LLM, and then correct that vulnerability in order to ensure here a set of properties, right, to have systems that are robust, achieve correctness, systems that are explainable, right, because the case of the AI. And that's what the vision that we have set here for our group is like to develop this platform for the next 10, 15 years, right? And as you can see, you always get a new building block, right, as part of this platform here. Yeah, that's the AI code that just to promote Eduardo Manino that works in my group in Manchester, right, that's gonna give a talk tomorrow. When you consider AI code, here are the state-of-the-art verifiers, okay? Eduardo has created a large here, not large like the Form AI, right? But he started, created like nearly 700 benchmarks in that domain of AI, right? Include here polynomial approximations, reinforcement learning, some mathematical functions, activation functions, and then with the ground truth, right? When they're safe and unsafe. And I believe the data set is balanced, yeah.
What is it that's being verified there?
Say again?
What is it that is being verified there? What do you...
Eduardo, maybe you can give a small,
These are in software verification jargon, these are reachability properties, but most data and safety properties are reachability. So I have to go a bit more deeper.
yeah, and they struggle, Haniel, in terms of understanding mathematical operations, the verifiers, right? I mean, there's a lot of floating point operations here, right? And as Eduardo is going to explain to more, and then with the trigonometric functions, right? Sin, cosine, and tan, age, and so on. And just in floating point. And then you can say, Lucas, I got this comment here from a colleague from Army to say that, well, for example, in the domain of aircraft, right? You work on that domain. Maybe you can tell us to say what it's true, what he told us. That, well, when they get this AI code and then they implement a software, they try to get rid of floating point. They do it as integers, right? Because there's a lot of things in terms of floating point operations, right, that are not defined well. And then since safety is of concern, right? So they avoid floating point and then focus on integers, and then so that they can achieve some sort of predictability of the code, right? Robustness and so on. But yeah, I'm not from so yeah.
I wouldn't be surprised.
Yeah.
What I have already heard from people that work on these developing safety critical systems for airplanes is that, for instance, they don't want concurrency.
They don't want concurrency.
So
and need a dynamic memory location.
So regarding concurrency, for instance, nowadays it's very difficult to process with a single core. So they buy a processor with multiple core, but they destroy the cores to keep just one working. So they don't want concurrency. So yes, I wouldn't be surprised if something that.
Yeah. Yeah. So anyway, we are focused on the floating point. They want to get it done. So then Eduardo's gonna give a work tomorrow, right? So here are the students, as I told you, I have like 5 PhD theses on top of this framework. The MS dissertations, GitHub, the final year project, so you can also see the data in GitHub. So most of these here are people from Manaus, Erickson from Manaus, Alessandro from Manaus, Yuri from Manaus, Felipe. Then I have Eduardo here, Rafael here as well, all right? So we have a mix here of people, of British people and Brazilian people in the group, right? That was a couple of award industrial deployments of this, a bit of the verification platform that we developed here that I have presented to you today, right? Acknowledgements.
I have a question.
Yeah. Good.
Regarding what Gustavo said, for self-driving cars, do you think that the spread issue would be what is blocking actually and really self-driving? So we can't prove it's going to be safe based on threat. Is that correct? You mentioned about that they buy these processors and destroy the cores and just leave it alone. The question is, they avoid threat for security reasons, right? So would that be the same with self-driving cars? Do you think that it applies that a self-driving car is not advancing that fast?
I think that there are other things that to be considered regarding regulation. So, for instance, when you are developing software that's going to be embedded in commercial airplanes, this is a sector that's regulated by some guides. So I have also heard that in the railway domain, for instance, it's not allowed to use some AI-powered software if you're going to work on something that's really safe. So I think that it also means, as I said, of the domain and the regulations that are involved. So maybe concerns cars, autonomous driving, would not have these regulation force prohibiting using these kind of techniques.
My impression is that there's also a question of culture. The use of formal methods in avionics has been developed for decades.
Yeah.
And it seems that in the self-driving car industry, which is just nascent, there's pretty little connection with what people are doing in avionics and in railways in terms of methods and simply culture. I don't think that the engineers are very aware of formal methods yet. We have something to do there.
One big difference is that machine learning methods for self-driving cars don't work yet. So there's no point of proving it's not working yet.
But as we know, when you develop a system and you hope at some point to have some high assurance, you have to think in those terms from day one.
Yeah. Yeah. Maybe we can have a discussion for the round table. Yeah. Yeah.
More questions?
So, no more questions? So let's thank Lucas for this really interesting course.
Yeah.
Thank you very much, Lucas.
Good. Yeah, thank you.
Tomorrow we have the workshop on automated.
Yeah, that maybe we can discuss further tomorrow.
Yeah, for more reason for trusted web AI systems. So I think that today we have kind of start.
Yeah, start discussion.
So it's going to be really exciting. So don't miss tomorrow. Lucas and I will be having the discussions, and you all guys invited to come. Okay, same time, same place. See you tomorrow then. Thank you very much indeed for the first day. See you tomorrow.
See you. Cadê o Sérgio Campos? Tá vindo, né? Tá, já chegou.